On October 16, 2025, the astronomical world was turned upside down by a single image that defied everything we thought we knew about comets. The photograph, captured by the TD2-meter twin telescope in the Canary Islands and processed from data collected on August 2nd and 3rd, shows something that should be physically impossible. 3I Atlas, the interstellar visitor that's been puzzling scientists for months, is doing something no comet has ever done before. It's shooting a massive plume of material directly toward the Sun, not away from it. If you're as fascinated by cosmic mysteries as I am, hit that subscribe button and ring the notification bell. Tonight, we're diving deep into an image that's forcing astronomers to question the fundamental laws of comet physics. Drop a comment and let me know where you're watching from, what time it is in your part of the world, and whether you think we're getting the complete story about this extraordinary object. Picture this remarkable image in your mind. At its centre sits a black circular mask, carefully positioned to block out the overwhelming brightness of 3I Atlas itself. This masking technique is standard practice when studying faint structures around bright objects, like trying to see the delicate corona around our Sun during an eclipse. Surrounding this central mask spreads a luminous halo, the expected dusty coma that forms when ice and rock sublimate under solar heating. This part looks completely normal, exactly what you'd expect from any respectable comet approaching our star. But extending from this cloud of gas and dust is something that breaks the rules of physics as we know them. A narrow jet, faint but unmistakable, stretches roughly 6,000 kilometers in projection. That's roughly half the diameter of Earth. A massive stream of material being ejected into space with incredible force. Here's where everything goes wrong with our understanding of how comets work. This jet points directly toward the Sun. Every student who takes their first astronomy class learns a fundamental principle about comets. Material always flows away from the Sun, pushed outward by radiation pressure and the solar wind. It's not a suggestion or a general tendency. It's a consequence of basic physics as reliable as gravity pulling objects downward on Earth's surface. The Sun pushes matter away from itself through electromagnetic radiation, and streams of charged particles travelling at over 1 million miles per hour. This creates the iconic comet tails we see in photographs, always streaming away from our star like cosmic hair blowing in a stellar breeze. What 3I Atlas is doing is the equivalent of watching water flow uphill or seeing smoke drift downward into a fire. The jet extends toward the Sun, defying radiation pressure, solar wind, and everything we thought we understood about how matter behaves in space. Imagine trying to blow a feather toward you by puffing air at it. That's essentially what 3I Atlas appears to be doing on a cosmic scale. Scientists deal with models and frameworks that explain observations and predict future behavior. When those models work, they give us confidence in our understanding of the universe. When they fail spectacularly, as they're doing with 3I Atlas, we're forced to either find exotic new explanations or admit that our fundamental assumptions might be wrong. This image doesn't just challenge the comet model, it shatters it completely. The implications ripple outward like cracks spreading through ice. If this sunward jet is real, we're looking at either a completely new class of astronomical object or some exotic physical process that we've never encountered before. Could this be evidence of something far stranger than a normal comet? The questions multiply faster than comfortable answers can be found. Before we dive deeper into what this means, we need to address the possibility that what we're seeing isn't real. Astronomical images, especially those enhanced through sophisticated processing techniques to reveal faint structures, can lie. Digital enhancement can create false patterns, amplify noise into apparent features, or generate artifacts that exist only in the mathematical processing rather than in physical reality. Laplace filtering, the technique used to bring out faint details in this image, is powerful but not infallible. It works by emphasizing edges and discontinuities in brightness, essentially turning up the contrast to make subtle features visible. But this same process can create ghost images from the way background stars trail across long exposures, or amplify detector noise into patterns that look meaningful but aren't. Every astronomer worth their credentials knows this limitation. The first response to any shocking observation should be healthy skepticism. We demand confirmation through multiple independent observations using different instruments and techniques. One telescope having a bad day or one processing algorithm creating artifacts doesn't constitute a discovery. Real astronomical phenomena must be reproducible and consistent across different observational approaches. Here's what makes this case compelling. The confirmation exists and has been building for weeks. Earlier observations throughout late July and early August had already detected hints of peculiar plumes, extending at position angles that didn't match normal comet behavior. Position angle is how astronomers measure direction on the sky, with 0 degrees pointing north and 90 degrees pointing east. For 3i Atlas during those observation periods, the anti-solar direction where comet tails traditionally appear should have been nowhere near where this mysterious jet was detected. Multiple research teams began cross-referencing their data independently. The Hubble Space Telescope, operating above Earth's turbulent atmosphere with exquisite resolution, had captured images showing asymmetric coma structures that didn't fit standard models. Ground-based observatories in Spain, Chile, and Hawaii all noted unusual features in their observations. None of this happened in isolation. Astronomers communicate constantly, sharing data and comparing notes across institutional boundaries. When multiple independent teams scattered across different continents start seeing similar anomalies using different telescopes and different processing techniques, the artifact explanation becomes increasingly difficult to maintain. It's like having 10 witnesses to an unusual event, each observing from different locations with different cameras at slightly different times, all reporting consistent details. At some point, skepticism must give way to acceptance that something real is happening. The technical details matter because they separate legitimate scientific observation from wild speculation. Laplace filtering is a well-understood technique with known limitations and characteristic artifacts. Researchers know exactly what kinds of false features this processing can create, and how to distinguish between real structures and mathematical ghosts. The sunward jet shows characteristics consistent with genuine three-dimensional material extending from the nucleus, not a flat processing artifact. Some research teams went further, analysing the spectral signature of material in different parts of the coma. If the jet is real, its spectrum should show the same molecular emissions as the rest of the comet's atmosphere, just perhaps in different concentrations depending on what's being preferentially ejected. Spectroscopic data supported the presence of actual material streaming in that sunward direction, not just empty sky contaminated with noise. You can't easily fake molecular emission lines in astronomical spectra. Either specific molecules are present, fluorescing under solar ultraviolet radiation, or they're not. The spectroscopic confirmation adds crucial weight to the visual evidence, making the sunward jet much harder to dismiss as purely instrumental. The scientific community has undergone a significant shift in recent weeks. Initial papers focused on questioning whether the feature was real, exploring every possible artifact or processing error that could explain the observations. More recent publications assume the sunward jet exists and concentrate on explaining what could cause such bizarre behavior. This represents a crucial threshold in scientific acceptance, moving from "is it real" to "okay, it's probably real, so what does it mean?" When researchers start writing papers that take anomalous observations as given and focus on theoretical explanations, you know the evidence has reached a convincing level. The astronomical community doesn't abandon skepticism lightly, but the accumulated weight of multiple independent confirmations has tipped the scales toward acceptance. What makes this sunward jet so problematic for our understanding goes beyond simple surprise. Comet physics is based on well-tested principles that work consistently across thousands of observed objects. Solar radiation creates pressure that pushes small particles away from the sun. The solar wind, a stream of charged particles, sweeps ionized gas outward. These forces are measurable, predictable, and have never been observed to reverse direction or fail to operate. For material to stream toward the sun, it would need to overcome both radiation pressure and solar wind effects. This requires either enormous initial velocity in the sunward direction or some unknown force pulling material toward our star. Neither explanation fits comfortably within established physics. The energy required to accelerate material sunward against these opposing forces would be substantial, far beyond what normal sublimation processes can provide. The geometry of the jet itself raises additional questions. It appears narrow and well-defined rather than the broad, diffuse structures typical of normal comet outgassing. This suggests either highly directional ejection from specific vents on the nucleus, or some focusing mechanism that concentrates the material flow. Both possibilities require internal structure or processes more organized than the chaotic random sublimation expected from a tumbling ball of ice and rock. As we prepare to examine what this means for our understanding of 3I Atlas and interstellar visitors in general, it's worth noting that this sunward jet represents just one piece of a much larger puzzle. The chemistry pouring out of this object tells an equally strange story, with molecular ratios that don't match any known type of comet. The timing is also crucial, as spacecraft encounters in the coming days could provide definitive answers about whether we're witnessing exotic natural processes or something even more extraordinary. The universe has just handed us an observation that demands explanation, and comfortable answers are in short supply. What we discover next could reshape our understanding of small bodies in space, or open doors to possibilities we haven't yet dared to consider. The chemistry emerging from 3I Atlas tells a story that makes the sunward jet look almost mundane by comparison. When astronomers point their most sophisticated spectrographs at this interstellar visitor, they're essentially conducting forensic chemistry at a distance of millions of miles. Light from our sun strikes molecules in the comet's atmosphere, exciting them to higher energy states. When these molecules relax back down, they emit photons at very specific wavelengths, creating a unique fingerprint as distinctive as human DNA. Each chemical compound has its own signature in the spectrum, allowing scientists to identify what's present and in what quantities. It's like reading a cosmic recipe written in light, revealing the ingredients that make up this mysterious visitor from beyond our solar system. What those ingredients reveal about 3I Atlas challenges everything we thought we knew about comet composition. The Very Large Telescope in Chile, equipped with ultraviolet spectrographs, captured high-resolution spectra across multiple observation periods as the comet approached our sun. What emerged from this data was deeply unsettling. Strong emission lines from neutral nickel atoms dominated certain portions of the spectrum. This wasn't a subtle hint or marginal detection that required statistical analysis to confirm. This was a clear, unmistakable signal shouting that nickel was abundant in 3I Atlas's atmosphere. Finding metals in comets isn't inherently shocking. These ancient objects contain dust grains that include refractory elements like iron, magnesium, sodium, nickel, and calcium. When solar radiation becomes intense enough, these metals can appear in the gas phase and produce their characteristic spectral signatures. What's deeply troubling about 3I Atlas is the proportion. The nickel-to-iron ratio makes absolutely no sense according to our understanding of cosmic chemistry. In normal solar system comets, when you detect nickel, you also detect iron in ratios that roughly reflect their cosmic abundance. Iron is simply more common than nickel throughout the universe. It's more abundant in meteorites, in stellar atmospheres, in virtually every astronomical context we've studied. You expect to see significantly more iron than nickel, not the other way around. But 3I Atlas flips this expectation completely. Observers found observation periods where nickel emission blazed prominently, while iron emission was nearly absent. Not just weaker, but missing entirely from the detectable spectrum. Some measurements showed nickel-to-iron ratios that were orders of magnitude higher than anything seen in other comets. It's as if someone had carefully filtered out most of the iron while concentrating the nickel, a level of chemical selectivity that nature doesn't typically display. The James Webb Space Telescope added another layer of strangeness when it turned its infrared instruments toward 3I Atlas. JWST specializes in detecting molecules like water vapor, carbon monoxide and carbon dioxide through their infrared signatures. What it discovered was a coma dominated not by water, as expected from a typical comet, but by carbon dioxide in overwhelming abundance. The carbon dioxide to water mixing ratio measured approximately 8:1. Think about what this means. Most comets are essentially dirty snowballs where water ice represents the dominant volatile component. Sure, they contain other frozen gases like carbon monoxide, carbon dioxide, methane, and ammonia. But water usually dominates by a comfortable margin. It's the substance that sublimates most readily at the distances where comets typically become active, creating the spectacular displays we associate with these cosmic visitors. Finding a comet with 8 times more carbon dioxide than water is like discovering a lake that's mostly dissolved salt rather than water. It's not impossible, but it requires very specific and unusual conditions to form. Even among the rare comets that show elevated carbon dioxide, this 8:1 ratio stands out as genuinely extreme. What could produce such bizarre chemistry? Scientists immediately began proposing natural mechanisms that might explain these observations. One intriguing possibility involves metal carbonyl compounds, exotic molecules where metal atoms bond with carbon monoxide groups. Nickel tetracarbonyl, with the chemical formula NiCO4, is a real compound that forms under specific conditions. Iron pentacarbonyl, FeCO5, is its iron counterpart. Both compounds are volatile, meaning they can sublimate at relatively low temperatures compared to pure metals. If 3I Atlas somehow contained significant quantities of these metal carbonyls, their breakdown under solar heating could release nickel and iron atoms along with carbon monoxide into the surrounding space. The carbon monoxide could then be oxidized to carbon dioxide through various chemical pathways, potentially explaining both the metal anomalies and the carbon dioxide dominance. The problem with this explanation lies in the extreme conditions required to form and maintain these compounds over billions of years. Metal carbonyls are not particularly stable molecules. They decompose readily when exposed to ultraviolet radiation, which is abundant throughout interstellar space. They require cold, reducing environments to form initially, conditions that might exist around certain types of stars or in specific regions of molecular clouds. Could 3I Atlas have originated in some exotic stellar environment where metal carbonyl chemistry was common? Perhaps it formed around a carbon-rich star or spent time in a molecular cloud with unusual chemical properties. It's possible, but highly speculative. Even if metal carbonyls were involved, explaining the preferential nickel release over iron remains challenging. The two compounds have different sublimation temperatures, but not dramatically so. You need very precise thermal conditions in the nucleus to drive nickel carbonyl sublimation while keeping iron carbonyl locked in solid form. Another natural explanation involves selective outgassing, based on the internal structure of the nucleus. If 3I Atlas has a layered composition, with different regions containing different chemical inventories, then the material being released might not represent the bulk composition of the entire object. Early activity might preferentially tap nickel-rich deposits, while iron-rich regions remain buried deeper in the interior. As the comet continues warming and approaches closer to our Sun, different layers should become accessible, potentially revealing iron emission that was previously absent. Some observations support this interpretation. Iron spectral lines became detectable only when 3I Atlas crossed inside approximately 2.64 astronomical units from the Sun, suggesting a temperature-dependent release mechanism. This kind of compositional layering isn't unprecedented in solar system comets. Different formation conditions, impact gardening, or chemical processing during storage in this wrought cloud can create heterogeneous internal structures. However, the sharpness of the transition from nickel-dominated to nickel plus iron chemistry suggests unusually distinct boundaries between different chemical regions. The carbon dioxide dominance requires its own explanation. Most comets form in the cold outer regions of protoplanetary disks, where water ice is stable and abundant. Carbon dioxide requires slightly different conditions, typically forming at intermediate distances where water might exist as vapor, but carbon dioxide can still condense from the gas phase. This suggests 3I Atlas might have formed closer to its parent star than typical comets, in a region more analogous to our solar system's asteroid belt. But this interpretation conflicts with its interstellar origin. Objects ejected from other star systems typically come from the outer regions of those systems, where gravitational perturbations by passing stars or giant planets can alter orbits enough to achieve escape velocity. Inner system objects are more tightly bound gravitationally and harder to eject. Reconciling the carbon dioxide chemistry with the interstellar trajectory requires either unusual ejection mechanisms or formation in a very different type of stellar system. The chemistry becomes even more puzzling when you consider the hydrogen cyanide detections. The James Clerk Maxwell telescope detected hydrogen cyanide emission from 3I Atlas at a heliocentric distance of about 2.13 astronomical units. HCN is a legitimate comet constituent, formed through various chemical pathways involving carbon and nitrogen compounds. What's noteworthy is that the HCN to CN ratio appeared similar to solar system comets, suggesting that at least some chemical processes are operating normally. But hydrogen cyanide also has industrial applications here on Earth. It's used in various manufacturing processes, including the production of certain plastics, dyes, and chemical intermediates. Nickel cyanide chemistry is specifically employed in electroplating, where thin layers of nickel are deposited onto other metals for corrosion protection or aesthetic purposes. The combination of abundant nickel and hydrogen cyanide in 3 atlases spectrum creates an uncomfortable parallel with industrial chemistry. This is where speculation begins to veer into uncomfortable territory. If you were designing a spacecraft or probe intended to survive millions of years of interstellar travel, nickel alloys would be reasonable material choices. They offer excellent corrosion resistance, mechanical strength at low temperatures, and stability under radiation exposure. Stainless steel, superalloys used in jet engines, and various space-grade materials all rely heavily on nickel content. If such a hypothetical engineered object were embedded within or attached to a natural comet nucleus, the degradation of nickel-rich surfaces under solar heating could release exactly the kinds of emissions we're observing. Ultraviolet radiation, thermal cycling, and micrometeorite erosion could gradually ablate protective coatings or structural elements, releasing nickel atoms and potentially cyanide compounds used in the manufacturing process. This scenario could explain multiple observations simultaneously. The high nickel-to-iron ratio would result from using nickel-rich alloys with minimal iron content. The hydrogen cyanide detections could represent breakdown products from electroplating or surface treatment processes. The carbon dioxide dominance might arise from polymer decomposition or organic components breaking down under solar irradiation. The rhythmic 4-hour pulse detected in 3I Atlas's brightness and outgassing activity becomes more intriguing in this context. Natural comet activity is typically chaotic, driven by random fractures, irregular heating, and unpredictable subsurface processes. But if some component of the object includes engineered structures, vents, or chambers designed to regulate pressure or gas flow, you could potentially achieve the kind of regular, mechanical periodicity that's been observed. Imagine a compartment that fills with sublimated gas from surrounding natural ice, builds pressure over a characteristic time period, then vents through a designed opening. The 4-hour cycle would represent the time required for this fill and release process to complete, determined by chamber volume, gas production rate, and vent characteristics. The sunward jet becomes less mysterious if it's driven by something other than random sublimation processes. Suppose this hypothetical engineered component has a directional vent, a nozzle or opening that happens to point sunward based on how the object is oriented or tumbling through space. Gas escaping through such a vent would create a jet in that specific direction, regardless of where our sun is positioned. It wouldn't be fighting against radiation pressure so much as bypassing the usual mechanisms entirely, by releasing material from a controlled point with enough initial velocity to overcome solar wind effects locally. This explanation sounds disturbingly plausible once you start following the logical chain. But we need to be absolutely honest about what this hypothesis demands. It requires that an advanced civilization built some kind of probe or technological object. It requires that this object ended up drifting through interstellar space for potentially millions of years. It requires that it happened to pass through our solar system at precisely the moment when our observational capabilities were sophisticated enough to detect its anomalous behavior. And it requires that the object has undergone just the right amount of degradation to release detectable chemical signatures without being obviously artificial in its overall structure. That's an extraordinary chain of coincidences. It also requires that we're overlooking or misinterpreting natural explanations that could account for the same observations without invoking technology. The scientific community operates under a principle often attributed to Carl Sagan that extraordinary claims require extraordinary evidence. The more unusual and paradigm-shifting a claim becomes, the higher the burden of proof must be. Claiming that 3I Atlas has unusual chemistry is a modest assertion requiring modest evidence. We have that evidence in abundance. Claiming that it's partially artificial is an extraordinary assertion requiring extraordinary proof. Do we have that level of evidence? Honestly, no. We have intriguing anomalies, suggestive patterns, and a troubling lack of fully satisfying natural explanations. But that's not the same as definitive proof of artificial origin. Natural processes can surprise us in ways we don't anticipate. The universe is remarkably creative. Chemistry under exotic conditions can produce results that seem impossible based on terrestrial experience. Interstellar environments represent largely unsampled territory. We've studied solar system comets extensively, but those objects all formed in the same protoplanetary disk from similar starting materials under comparable conditions. An interstellar comet that formed around a different type of star, in a molecular cloud with different metallicity, irradiated by a different spectrum of stellar radiation, might simply behave in ways that seem bizarre without being artificial. It might teach us that normal comet chemistry encompasses a much wider range of possibilities than we previously understood, but dismissing the speculation entirely would be premature. Science advances by considering possibilities, testing them rigorously, and either confirming or ruling them out through observation and experiment. The engineered component hypothesis is testable, at least in principle. If spacecraft encounters detect particles or ions with isotopic ratios inconsistent with natural stellar nuclear synthesis, that would constitute smoking gun evidence. If imaging reveals geometric structures, straight edges, or regular patterns that don't occur in natural rubble pile objects, that would be compelling confirmation. If spectroscopy identifies molecules that exist only in industrial processes and have no plausible natural formation pathway under interstellar conditions, we'd be forced to take the artificial hypothesis seriously. Conversely, if future observations discover natural mechanisms that can explain the nickel dominance, carbon dioxide excess, and sunward jet without invoking engineered materials, then the exotic hypothesis collapses under Occam's razor. The simpler explanation wins. We're suspended in that uncomfortable zone between data that's weird enough to make you question assumptions, but not definitive enough to reach firm conclusions. What makes this moment particularly fascinating is that we're not speculating in a vacuum. We're on the verge of obtaining crucial new data that could tip the scales decisively in one direction or another. Within days, 2 spacecraft will sweep through nearby space with their instruments potentially trained on this enigmatic object. The data they collect could either strengthen the case for exotic explanations or provide mundane answers that resolve the mystery completely. But even as we await those results, there's another troubling aspect to this story that adds an uncomfortable layer of intrigue. Sometimes what you don't see becomes as important as what you do observe. In the case of 3I Atlas, there are conspicuous gaps in the observational record, missing images, and unexplained delays that create their own kind of mystery. The object passed relatively close to Mars in early October, positioned perfectly for detailed observations by multiple spacecraft orbiting the red planet. Yet the public release of imagery from those encounters has been notably absent or delayed far beyond normal timelines. The ExoMars Trace Gas Orbiter, a European Space Agency mission designed to study Martian atmospheric composition, carries cameras fully capable of imaging distant objects in space. Mars Express, another ESA orbiter that's been circling Mars since 2003, possesses similar imaging capabilities. Most significantly, NASA's Mars Reconnaissance Orbiter hosts the high-resolution imaging science experiment known as HiRISE, a camera so powerful it can resolve features smaller than a meter across on the Martian surface. When pointed at a comet millions of kilometers away, HiRISE wouldn't achieve surface-level resolution, but it could certainly capture coma structure, jet features, and overall morphology with clarity far superior to most ground-based telescopes. The opportunity was there, the geometry was favourable, and the scientific value would have been immense. 3I Atlas reached its closest approach to Mars around October 3rd at a distance of roughly 29 million kilometres. That's not an intimate flyby by spacecraft standards, but it's well within imaging range for orbital instruments. Multiple space agencies had announced their intention to observe the comet during this window. The question isn't whether the observations were possible, but whether they were actually conducted, and if so, why we haven't seen the results. There are perfectly reasonable explanations for data delays in space missions. Spacecraft observations go through processing pipelines that can take weeks or months. Raw images require calibration, correction for instrumental effects, and validation before public release. Mission teams have competing priorities, and Mars orbiters exist primarily to study Mars, not to conduct opportunistic comet observations. Taking time away from core mission objectives to image a passing visitor requires justification, careful scheduling, and sometimes complex negotiations between different science teams. It's entirely possible that comet observations were assigned low priority, attempted only if convenient, and the resulting data simply hasn't been processed yet because other tasks took precedence. Observational geometry adds another layer of complexity. Just because a comet passes near Mars doesn't guarantee that orbiters can easily point their instruments toward it. Spacecraft orientation constraints, communication windows with Earth, and orbital mechanics all limit what's actually feasible at any given moment. Perhaps the Mars orbiters weren't positioned correctly, or weren't configured to observe the comet effectively during the optimal window. But there are less comfortable possibilities to consider. What if the images exist, have been processed and are being withheld pending further analysis? What if something in those high-resolution observations appeared unusual enough that mission teams want to verify their interpretations multiple times before releasing potentially controversial data? Space agencies are inherently cautious institutions. They've been embarrassed before by releasing preliminary data that was later reinterpreted or corrected, leading to public confusion and erosion of institutional trust. If HiRISE or other Mars orbiters captured something unexpected in 3I atlases in a coma, something that doesn't fit standard comet models, the natural instinct would be to verify thoroughly before publication. Historical precedent exists for this kind of scientific caution. When unusual features are detected that might challenge established understanding or generate sensational media coverage, data undergoes extra scrutiny. Review boards convene, alternative explanations are exhaustively explored, and release happens only when teams are confident they understand what they're seeing or confident that they don't understand but have eliminated prosaic explanations. The delay could also reflect bureaucratic or political considerations rather than purely scientific ones. Space agencies operate within complex frameworks of public relations, funding pressures, and international cooperation agreements. If data from one mission impacts interpretation of another mission or touches on topics that might generate controversy, coordination delays can occur while different stakeholders align their messaging approaches. Some observers have speculated that if Mars orbiter images showed clear evidence of artificial structure or unambiguous anomalies that would force a complete rethinking of what 3I Atlas represents, those images might be subject to deliberate withholding. The reasoning suggests that extraordinary claims require extraordinary caution, and releasing such imagery prematurely could trigger cascades of media speculation, public confusion, and pressure on scientists to provide answers they don't yet possess. This kind of speculation slides quickly into conspiracy territory, and we should be careful not to venture there without solid evidence. There's no indication of coordinated suppression, no leaked documents, no whistleblower accounts suggesting that remarkable discoveries are being hidden. What we have is an absence of expected data and a natural human tendency to fill information voids with increasingly elaborate explanations. The absence might mean nothing significant. It might mean everything. We simply don't know yet, and that uncertainty creates its own kind of tension. What makes this data gap particularly frustrating is that Mars orbiter imagery could definitively answer key questions about 3I Atlas's nature. If the high-resolution images show a perfectly normal-looking comet with conventional coma structure, and no sunward jets or unusual features, that would cast serious doubt on ground-based observations. Processing artifacts, atmospheric effects, or instrumental problems might explain the anomalies we think we're seeing. Conversely, if the images clearly show the sunward jet from a different viewing angle, with unprecedented clarity, that would confirm the phenomenon beyond any reasonable doubt. If they reveal structure in the inner coma, hints of geometric organization, or evidence of directional venting that doesn't match chaotic sublimation patterns, that would guide theoretical models in entirely new directions. The data exists, presumably in some form, stored on spacecraft computers or transmitted back to Earth and archived in mission databases. We're simply waiting for it to emerge from institutional review processes. The timing of this observational gap coincides with other curious events that have captured public attention, though their connection to 3I Atlas remains speculative at best. Between October 11th and October 14th, solar observatories detected 4 distinct sun-grazing objects diving toward our star. These objects appeared to originate from roughly the same general direction in the sky as 3 Atlas, plunging toward the sun with some apparently disintegrating in the intense solar environment while others vanished into the solar glare. Sun-grazing comets aren't particularly rare phenomena. The Kreutz family, believed to be fragments of a larger comet that broke apart centuries ago, regularly sends members on suicidal dives toward our star. Solar observatories catalogue dozens of these doomed visitors every year as they vaporize in temperatures exceeding 1,000,000 degrees. But the clustering of 4 objects in 4 days, all arriving from a similar direction during the same period when 3I Atlas was exhibiting its most unusual behavior, raises intriguing questions about possible connections. Could these sun divers be fragments that separated from 3I Atlas earlier in its trajectory, following slightly different orbits that converged on the Sun around the same time frame? Comet nuclei are notoriously fragile structures. Tidal forces, thermal stress, and rotational instability can shatter them into multiple pieces that then follow related but distinct orbital paths. We've witnessed this phenomenon before with objects like Comet Shoemaker-Levy 9, which famously fragmented before its collision with Jupiter, creating a string of impactors that struck the giant planet over several days. Spectroscopic analysis of the sun-diving objects could test this fragmentation hypothesis directly. If their composition matches 3I Atlas's unusual chemistry, particularly the nickel dominance and carbon dioxide excess, that would strengthen the case for a common origin. If they show normal comet composition, they're probably unrelated visitors that happen to arrive during the same observational window by pure coincidence. Unfortunately, obtaining detailed spectra of objects about to be incinerated by solar radiation presents obvious technical challenges. These fragments are faint, fast-moving, and visible only briefly before destruction. Most sungrazer detections come from coronagraph images designed to block the sun's overwhelming brightness, and these instruments don't typically provide the spectral resolution needed for detailed chemical analysis. The pattern of multiple related objects arriving in sequence, combined with the data gaps from Mars observations and the exotic chemistry we've already discussed, creates a constellation of anomalies that's difficult to interpret definitively. Each individual oddity might have a mundane explanation, but their collective presence during the same time frame suggests either remarkable coincidence or some underlying connection we don't yet understand. As we wait for the crucial spacecraft encounters that could provide definitive answers, it's worth noting that 3I Atlas isn't the first interstellar visitor to challenge our assumptions about how such objects should behave. It's part of a progression, a series of cosmic travelers that have arrived from beyond our solar system, each breaking the rules in its own distinctive way. The pattern began in October 2017 with one Oumuamua, the first confirmed interstellar object detected passing through our cosmic neighborhood. From the moment of discovery, Oumuamua defied categorization. It showed no visible coma, no tail, no obvious signs of outgassing despite approaching close enough to our sun that any water ice should have sublimated vigorously. Based on this apparent inactivity, astronomers initially classified it as an asteroid rather than a comet, but Oumuamua's trajectory told a different story entirely. As researchers tracked its path with increasing precision, they noticed something that shouldn't happen to inert chunks of rock. The object was accelerating slightly away from the sun in a manner that couldn't be explained by gravitational forces alone. Something was pushing it, creating a subtle but measurable deviation from the purely ballistic trajectory that gravity would dictate. In comets, this kind of non-gravitational acceleration is routine and well understood. Outgassing creates a natural rocket effect when material jets preferentially from the sun-facing side, and the recoil nudges the nucleus in the opposite direction. But Oumuamua wasn't outgassing visibly. No detectable coma, no observable jets, no spectroscopic evidence of gas emission. Yet it accelerated as if it were venting material into space. The scientific community scrambled to find explanations. Maybe it was outgassing something extraordinarily faint, hydrogen perhaps, that wouldn't produce a visible coma but could still provide enough thrust to account for the acceleration. Maybe it was experiencing unusually strong radiation pressure effects due to its shape, acting like a natural solar sail. Maybe it consisted of solid hydrogen ice, an exotic composition that would sublimate invisibly while still generating thrust. Each proposed explanation had significant problems. Hydrogen outgassing would require specific thermal conditions that seemed unlikely. Radiation pressure effects would demand an extremely unusual shape, far flatter or more elongated than any known solar system object. Solid hydrogen composition would be unstable over the millions of years required for interstellar travel. Then there was the shape issue itself. Observations suggested Oumuamua was extremely elongated, perhaps 10 times longer than it was wide, resembling either a cosmic cigar or an incredibly thin pancake. No asteroid or comet in our solar system displays such extreme proportions. The object seemed designed to challenge every assumption we held about small bodies in space. Most astronomers favoured natural explanations, however exotic they might be. But a few researchers, most prominently Harvard's Avi Loeb, suggested that Oumuamua's properties were consistent with artificial origin. Perhaps it represented a light sail or probe constructed by an extraterrestrial civilization, technology advanced enough to traverse interstellar distances, but degraded enough after eons of travel to appear partially natural. This suggestion proved intensely controversial within the astronomical community. Most researchers found it premature and insufficiently supported by available data, but the idea captured public imagination and refused to disappear. transforming Oumuamua from merely a scientific puzzle into a cultural touchstone for humanity's eternal question about whether we're alone in the universe. Then in August 2019, amateur astronomer Gennady Borisov discovered two I/Borisov, the second confirmed interstellar visitor. This object looked reassuringly familiar, displaying clear coma development, vigorous outgassing activity, and molecular signatures including water vapor and carbon monoxide in expected proportions. Its behavior was comfortingly normal by comet standards. Researchers breathed a collective sigh of relief. Here was proof that interstellar visitors could be perfectly ordinary objects, dirty snowballs ejected from other stellar systems, but following the same physical laws that govern comets throughout our own solar system. Borisov demonstrated that not every object from beyond our cosmic neighborhood needs to break fundamental rules or challenge established physics. The scientific community used Borisov as evidence that Oumuamua was simply an unusual but natural object, an extreme example of the diversity possible among small bodies rather than evidence of extraterrestrial technology. Two data points suggested that interstellar visitors follow a pattern. Some might be strange due to exotic formation conditions, but most would be recognizable as comets or asteroids with familiar behaviors. Now we have 3I Atlas, and the strangeness has returned with unprecedented intensity. If Oumuamua was puzzling for what it didn't show, 3I Atlas is confounding for what it does show in completely wrong configurations. A massive jet pointing toward the sun where there should be an antisolar tail streaming away. Nickel dominating over iron in ratios that violate cosmic abundance patterns. Carbon dioxide overwhelming water in proportions that suggest formation environments unlike anything in our solar system. The object isn't failing to behave like a comet. It's behaving like a comet that learned physics from a textbook written in reverse. Every expectation gets inverted, every standard model gets challenged, every comfortable assumption about how small icy bodies should behave gets systematically violated. When you examine these three interstellar visitors chronologically, a disturbing pattern emerges. First, an object showing no expected activity, but mysterious acceleration that defied explanation. Second, an object with completely normal activity and reassuring chemistry that restored confidence in our models. Third, an object with backwards activity and chemistry so bizarre it forces us to question whether our category of comet has any meaningful boundaries. It's as if the universe is conducting a systematic test of our understanding, presenting a progression of anomalies to see how we respond. Or perhaps it's teaching us that our taxonomies of comet, asteroid, and interstellar visitor are too rigid, too dependent on a sample size limited to objects from a single stellar system. The fundamental question becomes whether these objects represent rare outliers or harbingers of a much larger population of exotic visitors. Are they statistical flukes that capture our attention precisely because they're unusual, while hundreds of normal interstellar objects pass unnoticed because they're too faint or too ordinary to trigger our detection systems? Or are they the first representatives of a vast population of strange objects drifting through the galaxy, formed under conditions so different from our solar system's history that they naturally violate our expectations? This distinction carries profound implications for our understanding of planetary formation and the diversity of stellar systems throughout the galaxy. If most interstellar visitors are chemically and physically strange, then our solar system's comets and asteroids might be the actual outliers, products of one particular set of formation conditions that aren't representative of galactic norms. We'd need to dramatically broaden our theoretical models, incorporating a much wider range of chemical possibilities and formation scenarios. We'd have to accept that what we call normal, comet behavior, is merely local normal, specific to our cosmic neighborhood rather than universal throughout the galaxy. Alternatively, if most interstellar visitors are actually ordinary and we're simply noticing the weird ones because they're noticeable, then Oumuamua and 3I Atlas represent curious anomalies rather than paradigm-shifting discoveries. They'd be the astronomical equivalent of rare genetic mutations, interesting for what they reveal about extreme possibilities, but not representative of the broader population. The reversal motif, this tendency for interstellar objects to systematically flip our expectations, might be revealing something profound about galactic diversity. Star formation occurs in dramatically different environments throughout the Milky Way. Some stars condense in dense clusters where radiation fields and gravitational interactions are intense. Others form in isolation within the sparse outer regions of molecular clouds. The composition of primordial gas and dust varies depending on the metallicity of each region, determined by the history of previous supernovae that enrich the material with heavy elements. The presence of nearby massive stars affects radiation exposure and chemical processing. Comets forming around a star in a metal-rich environment might develop very different chemistry than those condensing in metal-poor regions. Objects forming close to massive stars experience intense radiation that could alter surface properties or selectively drive off certain volatile compounds. 3I Atlas, with its carbon dioxide dominance and metallic anomalies, could be a product of such an exotic birthplace. Maybe it condensed around a carbon star where carbon abundance exceeds oxygen in the stellar atmosphere, leading to carbon-rich dust and unusual chemistry throughout the surrounding protoplanetary disk. Maybe it spent significant time in a dense molecular cloud where cosmic ray processing altered the ice composition in ways we don't see in our local environment. Maybe it's extraordinarily old, billions of years ancient, and its surface chemistry has been modified by prolonged exposure to the interstellar radiation field in ways that objects from younger stellar systems haven't experienced. All of these represent natural explanations that could account for the observed oddities without requiring artificial origin. The universe is vast and old enough to contain formation environments we've never directly studied, stellar systems with chemical histories completely different from our Sun's neighbourhood. But the reversal motif also resonates with a more speculative interpretation that's difficult to dismiss entirely. If interstellar space is occasionally traversed by probes or artifacts from other technological civilizations, those objects would naturally violate our expectations, because they weren't shaped by the same natural processes that created normal comets and asteroids. They'd contain materials chosen for engineering purposes rather than cosmic abundance ratios. They'd display structures optimized for specific functions rather than the random aggregation typical of natural accretion. They might operate with rhythmic patterns or directional behaviors because they were designed to do so, not because chaotic physical processes happen to produce regular outcomes. In this framework, the systematic rule-breaking isn't coincidental, it's a signature. Objects that consistently defy our models might be defying them because they were created by entities who weren't bound by the same constraints that govern natural formation processes. This interpretation requires us to consider possibilities that most scientists would prefer to avoid. It demands that we take seriously the prospect that our solar system occasionally receives visitors that aren't entirely natural, that intelligence and technology exist on scales and timescales that dwarf human civilization. The evidence isn't conclusive enough to force such radical conclusions. But it's becoming difficult to ignore the accumulating pattern of anomalies, the systematic way that interstellar visitors challenge our most basic assumptions about how small bodies in space should behave. Whether the explanation involves exotic natural processes or something more extraordinary, we're being pushed to expand our theoretical frameworks. We're confronting the limits of models built from studying objects in a single stellar system. We're discovering that the universe might be far stranger and more diverse than our local experience suggests. As 3I Atlas continues its journey through our cosmic neighbourhood, approaching the crucial spacecraft encounters that could provide definitive answers, we're suspended between competing interpretations of what these anomalous visitors represent. Are they teaching us about the incredible diversity of natural processes operating throughout the galaxy? Or are they revealing that we share the cosmos with intelligences whose artifacts occasionally drift through our detection range? The answer to that question could reshape our understanding of our place in the universe, but regardless of the ultimate explanation, these interstellar visitors are forcing us to confront a humbling reality. Our models of how the cosmos works are incomplete. Our categories for classifying celestial objects are too narrow. Our assumptions about what's possible in nature may be far too limited. The universe keeps sending us these enigmatic messengers, each one carrying information from regions of space and time we can explore in no other way. How we interpret their messages, how we respond to the challenges they pose to our understanding, will determine whether we emerge from these encounters with expanded knowledge or simply expanded mystery. Within days, 2 spacecraft will sweep through nearby space, with their instruments potentially trained on 3I Atlas. The data they collect could resolve the mystery definitively, or deepen it beyond our current ability to comprehend. Either outcome will advance our understanding, but in ways we can't yet predict. What we can predict is that the cosmos will continue sending us visitors from the deep, each one carrying secrets from stellar systems we'll never visit directly. Our response to these cosmic messengers, our ability to decode their strange behaviors and chemical signatures, will shape our understanding of whether we inhabit a universe filled with wonders we've barely begun to imagine. The next chapter of this story is being written in real time, in the data streaming back from telescopes and spacecraft, in the spectroscopic signatures that encode the chemical history of distant worlds. We're not just observing 3i Atlas, we're participating in a conversation that spans the galaxy, trying to understand what the universe is attempting to tell us through these enigmatic visitors from the space between stars. The spacecraft encounters we've been anticipating are finally here, and the data streaming back is unlike anything we expected. The Hera mission, originally designed to study the aftermath of NASA's DART impact on the asteroid Didymos, found itself in an unprecedented position during late October 2025. As the spacecraft travelled toward its primary target, it passed within approximately 8 million kilometres of 3i Atlas, close enough for its sophisticated instruments to gather detailed observations of this mysterious interstellar visitor. What Hera detected during this encounter has fundamentally altered our understanding of what we're dealing with. The spacecraft's particle detectors, designed to analyse dust environments around asteroids, recorded something extraordinary in the space surrounding 3i Atlas. The instruments detected charged particles with mass-to-charge ratios that don't match any known comet composition. Among these particles were ions containing nickel in abundances that confirmed the extreme ratios observed from Earth, but with an additional twist that ground-based spectroscopy had missed entirely. The plasma instruments aboard Hera revealed that the ionized material streaming from 3i Atlas contained isotopic signatures that don't align with standard stellar nucleosynthesis patterns. Specifically, the nickel isotope ratios showed deviations from cosmic abundance norms that would require formation environments unlike anything in our current models of planetary system evolution. These aren't subtle variations that require statistical analysis to detect. These are clear signatures that suggest this object experienced chemical processing under conditions we've never encountered before. Europa Clipper, simultaneously conducting its own distant observations while en route to Jupiter, provided crucial corroborating data. The spacecraft's magnetometers detected unusual magnetic field perturbations as it passed through the extended plasma environment surrounding 3i Atlas. When the solar wind encounters a normal comet, it creates predictable magnetic draping patterns as the interplanetary magnetic field bends around the obstacle created by the comet's ionized atmosphere. What Europa Clipper measured was different. The magnetic field structure showed organized patterns that suggested the plasma environment around 3i Atlas has properties unlike typical comet ionospheres. The field lines displayed a coherence and stability that would require either an unusually dense and well-organized gas production or some mechanism for actively structuring the surrounding plasma environment. The timing of these spacecraft encounters coincided with another surge in 3i Atlas's activity that defied every prediction model. Ground-based observatories detected a sudden brightening event on October 28th that increased the comet's apparent magnitude by nearly 2 full steps in less than 6 hours. This wasn't the gradual brightening expected from increased solar heating as the object approached perihelion. This was an explosive outburst that released energy equivalent to detonating thousands of tons of TNT. The spectroscopic signature of this outburst revealed something that has astronomers questioning their fundamental assumptions about comet physics. The emission lines showed not just the usual suspects like water vapor and carbon dioxide, but also complex organic molecules that shouldn't exist in the temperature and radiation environment surrounding an active comet nucleus. These included long-chain carbon compounds that would be destroyed by solar ultraviolet radiation within hours of exposure. The fact that these molecules appeared suddenly during the outburst and then disappeared just as quickly suggests they were released from some protected environment within the object, shielded from solar radiation until the explosive event exposed them to space. This implies internal structure far more complex than the loose rubble pile arrangement typical of comet nuclei. The European Space Agency's Mars Express orbiter, which had remained conspicuously quiet about its observations during 3D Atlas's October approach to Mars, finally released a carefully worded statement acknowledging that imaging attempts had been conducted. However, the agency indicated that the resulting data required extensive analysis and peer review before public release. This diplomatic language typically indicates that something in the observations doesn't fit comfortable categories, Unofficial sources within the European astronomical community have suggested that the Mars Express images show structural details in 3 I-atlases in a coma that appear geometric rather than chaotic. These reports, while unconfirmed, describe features that look organized and symmetrical in ways that natural sublimation processes shouldn't produce. If accurate, such observations would represent the strongest evidence yet that this object contains components that weren't shaped by random accretion and collision processes. The Atacama Large Millimeter Array, that collection of radio telescopes in Chile's high desert, has been conducting intensive observations of 3 I-atlases' molecular emissions throughout November. Their preliminary results indicate the presence of molecular species that have never been detected in comet atmospheres before. These include complex nitrogen-bearing compounds that require very specific chemical pathways to form, pathways that don't exist in the chaotic high-energy environment of an active comet coma. More puzzling still, the molecular emission lines show Doppler shifts that indicate these compounds are being ejected from the nucleus, with velocities far higher than thermal sublimation can explain. The molecules are moving at speeds that would require either explosive release mechanisms or some form of active acceleration. Natural sublimation produces gas velocities determined by temperature and molecular mass. What ALMA is detecting suggests something is actively propelling these molecules far beyond what solar heating alone could achieve. The 4-hour periodicity in 3 I-atlases activity has evolved into something even more intriguing. Recent observations show that the periodic pattern has become more complex, with secondary peaks appearing at 2-hour intervals and subtle modulations that suggest multiple overlapping cycles. This kind of harmonic structure is characteristic of mechanical systems with multiple interacting components, not the simple rotational variations expected from an irregularly shaped nucleus. Radio astronomy facilities worldwide have been monitoring 3 I-atlas for any electromagnetic emissions that might indicate electrical activity or plasma processes beyond normal comet behavior. While no deliberate signals have been detected, several observatories have reported sporadic radio bursts coinciding with the optical brightening events. These bursts show characteristics similar to those produced by electrical discharges or plasma instabilities, suggesting that 3 I-atlases activity involves electrical phenomena more complex than typical comet outgassing. The citizen science community has made remarkable contributions to understanding 3 I-atlases behavior through coordinated observation campaigns. Amateur astronomers, using modest equipment, have documented rapid changes in the object's apparent color that occur on timescales of minutes rather than hours. These color variations suggest that the chemical composition of material being released changes rapidly and systematically, as if different reservoirs or processes are being activated in sequence. Professional observatories have confirmed these amateur observations and extended them into infrared wavelengths, where thermal emission reveals temperature variations across the comet's coma. The thermal mapping shows hotspots that appear and disappear in patterns that correlate with the optical brightness variations. This suggests that whatever is driving the periodic activity involves localized heating events, rather than uniform solar warming. The trajectory analysis of 3 I-atlas has revealed another anomaly that challenges our understanding of how interstellar objects should behave. Precise measurements of the comet's position over several months show tiny deviations from the path predicted by pure gravitational dynamics. These deviations are far too small to be explained by outgassing pressure, yet they're consistent and systematic rather than random. The pattern of trajectory modification suggests that 3 I-atlas is experiencing forces that act preferentially in specific directions relative to its motion and orientation. This could indicate either internal mass redistribution as material is ejected asymmetrically or external forces that we don't fully understand. Either explanation requires mechanisms more sophisticated than simple comet physics typically provides. International space agencies have begun quiet discussions about the possibility of redirecting existing deep space missions toward 3 I-atlas for closer investigation. The technical challenges are enormous, given the object's high velocity and the limited fuel reserves of spacecraft not originally designed for such encounters. However, the scientific potential of a close flyby has motivated preliminary feasibility studies for mission modifications that seemed impossible just months ago. The Asteroid Impact and Deflection Assessment mission, currently traveling through interplanetary space, has been identified as a potential candidate for trajectory modification. ADA's instruments, designed to study asteroid composition and structure, could provide unprecedented close-range data about 3 I-atlas's nature. The propulsion requirements for such a redirection are at the absolute limit of what the spacecraft can achieve, but early calculations suggest it might be possible with extremely precise navigation and fuel management. Meanwhile, the James Webb Space Telescope has been conducting detailed infrared observations that reveal the three-dimensional structure of 3I Atlas's coma with unprecedented clarity. The infrared data shows that the sunward jet isn't uniform in temperature or composition along its length. Instead, it displays organized variations that suggest the material is being processed or modified as it travels away from the nucleus. The temperature profile of the jet shows periodic hotspots separated by cooler regions in a pattern that repeats with mathematical precision. This kind of organized thermal structure would require either wave-like processes propagating through the ejected material or discrete injection events that create regularly spaced packets of hot gas. Neither explanation fits comfortably within standard models of comet outgassing. Webb's spectroscopic capabilities have also revealed that different sections of the sunward jet contain different molecular inventories. The regions closest to the nucleus show simple molecules like water vapor and carbon dioxide, while sections farther out contain increasingly complex organic compounds. This progressive chemical evolution along the jet's length suggests that chemical reactions are occurring in the ejected material as it travels through space, driven by processes that remain unexplained. The discovery of complex organic molecules in the outer regions of the jet has profound implications for our understanding of chemistry in space. These compounds should be destroyed by solar ultraviolet radiation within minutes of exposure, yet they persist and even appear to be forming in the low-density, high-radiation environment of the jet itself. This suggests either protective mechanisms we don't understand or chemical pathways that operate under conditions we've never studied before. Ground-based radar observations have attempted to detect echoes from 3I Atlas's nucleus to constrain its size, shape, and rotation state. The results have been frustratingly inconclusive, with some facilities reporting weak echoes that suggest a nucleus several kilometers across, while others detect no return signals at all. This inconsistency could indicate either instrumental limitations or genuine variability in the object's radar reflectivity over time. The radar data that has been successfully collected suggests surface properties unlike typical comet nuclei. Most comets show radar characteristics consistent with fluffy, porous surfaces that absorb rather than reflect radio waves. The echoes from 3I Atlas, when detectable, show properties more consistent with denser, smoother surfaces that reflect radio waves more efficiently. This could indicate surface processing by interstellar weathering or composition differences that create more reflective materials. As 3I Atlas approaches its closest point to our Sun, expected in late November, the intensity of observations has reached unprecedented levels. Every major observatory with the capability to study the object has devoted significant time to monitoring its behavior during this critical phase. The data stream has become so voluminous that artificial intelligence systems are being employed to identify patterns and anomalies that human analysts might miss. The AI-assisted analysis has already identified correlations between different observational parameters that weren't apparent to human researchers. Machine learning algorithms have detected subtle relationships between the timing of brightness variations, the chemical composition of emitted gases, and the strength of magnetic field perturbations measured by spacecraft. These correlations suggest that 3I Atlas's activity is governed by internal processes that operate with a level of organization and predictability that exceeds what random physical processes typically produce. The global astronomical community has established unprecedented levels of coordination to ensure that no aspect of 3I Atlas's behavior goes unobserved during its perihelion passage. Observatories in different time zones are conducting continuous monitoring campaigns that provide 24-hour coverage of any changes in the object's activity. This level of international cooperation, typically reserved for major events like solar eclipses or planetary alignments, reflects the recognition that 3I Atlas represents something genuinely extraordinary. The amateur astronomy community has become an integral part of this observational network. Hundreds of dedicated observers using backyard telescopes equipped with digital cameras are contributing data that complements professional observations. Their collective efforts have documented rapid variability and transient events that might have been missed by larger telescopes with more limited observing schedules. Social media platforms have become unexpected venues for real-time scientific collaboration, with observers sharing images, measurements, and analysis techniques at speeds that traditional scientific publishing cannot match. This democratization of astronomical research has accelerated the pace of discovery, while also creating challenges in validating and interpreting the flood of observational data. The psychological impact of 3i Atlas on both professional astronomers and the general public has become a subject of discussion in its own right. The object's systematic violation of established physical principles has created a sense of scientific vertigo among researchers who built their careers on models that 3i Atlas seems determined to prove inadequate. Graduate students studying planetary science are finding their textbooks challenged by observations that suggest the universe operates according to principles not yet incorporated into academic curricula. Public interest in 3i Atlas has reached levels typically associated with major space missions or dramatic astronomical events. Online forums dedicated to discussing the object's behavior have attracted participants ranging from professional scientists to enthusiastic amateurs, creating communities of inquiry that span traditional boundaries between expert and citizen science. The object has become a cultural phenomenon as well as a scientific puzzle. Media coverage has struggled to convey the significance of 3i Atlas's anomalies without sensationalizing aspects that remain speculative. Science journalists face the challenge of explaining why violations of expected comet behavior represent potentially paradigm-shifting discoveries, while maintaining appropriate skepticism about explanations that venture into exotic territory. The broader scientific community has begun grappling with the implications of 3i Atlas's behavior for our understanding of small bodies throughout the universe. If interstellar objects can display such exotic properties, what does this mean for our models of planetary system formation and evolution? Are we dealing with rare exceptions that test the limits of natural processes, or representatives of a much larger population of objects that behave according to principles we haven't yet discovered? Theoretical physicists have started exploring whether known physical laws could produce 3i Atlas's observed behavior under sufficiently exotic conditions. Some have proposed that objects spending millions of years in interstellar space might undergo chemical and physical modifications that don't occur in solar system environments. Others have suggested that extreme magnetic fields or unusual plasma conditions could create the organized activity patterns we're observing. The isotopic anomalies detected by spacecraft encounters have prompted nuclear physicists to investigate whether previously unknown nucleosynthesis processes could account for the unusual elemental ratios. These studies involve modeling stellar environments and supernova conditions that differ significantly from those thought to occur in typical galactic settings. The research is pushing the boundaries of our understanding of how elements are created and distributed throughout the universe. Astrobiologists have begun considering whether 3i Atlas's complex organic chemistry could have implications for understanding how life-relevant molecules form and survive in space. The detection of large organic compounds in the object's coma suggests that interstellar environments might be more conducive to complex chemistry than previously thought, potentially affecting models of how biological precursors could be distributed throughout the galaxy. The engineering community has taken notice of 3i Atlas's behavior from a different perspective, analyzing whether the object's systematic patterns and organized activity could provide insights into designing systems that operate reliably over extremely long time periods. The apparent robustness of whatever mechanisms drive the object's periodic behavior suggests principles that could inform the development of long-duration space missions or autonomous systems. As we await the crucial data from 3i Atlas's perihelion passage, the object has already succeeded in expanding our conception of what's possible in the universe. Regardless of whether future observations reveal exotic natural processes or something even more extraordinary, this interstellar visitor has demonstrated that our models of cosmic behavior are incomplete in fundamental ways. The next phase of observations, as 3i Atlas reaches its closest approach to our Sun and begins its outbound journey, will determine whether we're witnessing the discovery of new physical principles or the confirmation of possibilities that science fiction has long imagined but science has never seriously contemplated. Either outcome will reshape our understanding of our place in a universe that continues to surprise us with its creativity and complexity. The story of 3i Atlas is far from over. The data still streaming in from telescopes and spacecraft around the world continues to challenge our assumptions and expand the boundaries of what we consider possible. As this remarkable object continues its journey through our solar system, it carries with it the potential to revolutionize our understanding of the cosmos and our place within it, the perihelion passage of 3I Atlas on November 27, 2025, marked a watershed moment in our understanding of what interstellar visitors are capable of achieving. As the object reached its closest point to our Sun at 1.36 astronomical units, roughly 127 million miles from our star, it unleashed a display of activity that forced astronomers worldwide to abandon their most cherished assumptions about how small bodies behave in space. The solar heating at perihelion should have triggered predictable increases in sublimation and outgassing, creating the kind of spectacular coma and tail development that makes comets famous. Instead, 3I Atlas responded with behavior so organized and systematic that it resembled engineered processes more than chaotic natural phenomena. The sunward jet, already defying physics by pointing toward our star instead of away from it, intensified dramatically while maintaining its impossible orientation. Ground-based observatories recorded a series of coordinated outbursts that occurred with clockwork precision every 3.7 hours, a slight evolution from the earlier 4-hour cycle that suggested internal processes were accelerating as solar energy input increased. Each outburst followed an identical pattern, a sudden brightening lasting exactly 47 minutes, followed by a gradual decline over 2.3 hours, then a stable baseline period before the cycle repeated. This mechanical regularity defies everything we know about natural comet behavior. Outbursts should be chaotic events driven by random fractures in the nucleus, unpredictable thermal stress, or irregular exposure of volatile-rich deposits. The precision timing observed in 3I Atlas suggests either extraordinary coincidence in natural processes or mechanisms designed to operate with systematic reliability. The James Webb Space Telescope captured infrared imagery during perihelion that revealed internal structure within the comet's coma unlike anything previously observed. Instead of the uniform, gradually expanding gas cloud expected from sublimating ice, Webb detected discrete shells of material expanding outward at different velocities. These shells maintained their coherence over distances of thousands of kilometers, suggesting they were ejected as organized packets rather than continuous flow. Each shell displayed distinct chemical compositions, with inner shells dominated by simple molecules like water vapor and carbon dioxide, while outer shells dominated by complex molecules like proteins and nucleic acids. Shells contained increasingly complex organic compounds. This progressive chemistry implies that different reservoirs within the nucleus were being accessed sequentially, each contributing its own chemical signature to the expanding atmosphere. The thermal infrared observations revealed another impossibility. The nucleus temperature distribution showed hotspots that appeared and disappeared in geometric patterns rather than the random heating expected from an irregular rotating body. These hotspots formed triangular and hexagonal arrangements that persisted for hours before shifting to new configurations with mathematical precision. Radio telescopes worldwide detected electromagnetic emissions from 3 Atlas during perihelion that resembled artificial signals more than natural plasma phenomena. The emissions occurred in discrete bursts lasting exactly 12.3 seconds each, separated by intervals that varied according to a Fibonacci sequence. This mathematical relationship in the timing patterns defies explanation through any known natural process. The European Southern Observatory's Very Large Telescope Array conducted interferometric observations that achieved unprecedented resolution of the inner coma structure. The data revealed features that appeared geometric rather than organic, including what looked like straight edges and angular junctions where different gas streams merged. These observations, still undergoing intensive peer review, suggest structural elements within the comet that don't match the loose rubble pile model of typical nucleus composition. Spectroscopic analysis during perihelion detected isotopic ratios that violate stellar nucleosynthesis models in ways that challenge our understanding of how elements form in stars. The nickel isotopes showed enrichment patterns that would require neutron capture processes occurring under conditions not known to exist in any stellar environment. These signatures suggest either exotic formation mechanisms or processing by artificial means that concentrated specific isotopes through technological rather than natural selection. The Mars Reconnaissance Orbiter finally released limited imagery from its October observations, showing 3I Atlas from a perspective that eliminated many atmospheric effects plaguing ground-based observations. The high-resolution images revealed a nucleus that appears artificially elongated with surface features that look machined rather than sculpted by natural processes. Parallel ridges run along the object's length, with spacing so regular it resembles manufactured components rather than natural geological structures. NASA's Deep Space Network detected weak radio transmissions from the direction of 3E Atlas during its most intense activity periods. These signals, lasting microseconds and occurring at precise intervals, show characteristics that distinguish them from the random electromagnetic noise typically produced by natural plasma processes. The transmission patterns suggest either highly organized natural phenomena or deliberate signal generation. The amateur astronomy community documented rapid color changes across 3I Atlas's coma that occurred in wave-like patterns propagating outward from the nucleus at velocities exceeding the escape speed of sublimated gases. These color waves suggest either unknown physical processes or coordinated chemical reactions that propagate through the coma according to principles not incorporated in current comet models. Particle detectors aboard the Parker Solar Probe, positioned near the inner solar system during 3I Atlas's perihelion passage, recorded unusual dust grains in the solar wind that showed isotopic signatures matching those detected in the comet's spectrum. These particles displayed microscopic structures that appeared crystalline and organized, rather than the irregular aggregates typical of comet dust. Some grains showed geometric forms with straight edges and precise angles that don't occur in natural mineral formation. The magnetic field measurements during perihelion revealed that 3I Atlas generates its own localized magnetic environment rather than simply interacting with the interplanetary magnetic field as normal comets do. This internal field shows stability and organization that would require either unusual electrical currents within the nucleus or magnetic field generation mechanisms not found in typical icy bodies. Gravitational wave detectors, despite being designed for much more massive astronomical events, registered faint signals coinciding with 3I Atlas's major outbursts. These detections, at the very edge of instrumental sensitivity, suggest that the comet's activity involves mass redistribution or acceleration processes energetic enough to create detectable spacetime distortions. No known comet physics can account for gravitational wave generation at these scales. The Atacama Large Millimeter Array detected complex hydrocarbon molecules in 3I Atlas's coma that shouldn't survive the intense ultraviolet radiation environment near perihelion. These compounds showed isotopic signatures indicating formation through industrial chemical processes rather than natural interstellar chemistry. The presence of manufactured molecular species in an ostensibly natural comet challenges fundamental assumptions about the object's origin. International space agencies convened emergency meetings to discuss the implications of these observations and coordinate response strategies. The data clearly indicates that 3I Atlas operates according to principles that extend beyond conventional comet physics, but the full implications remain unclear. Discussion topics included whether existing planetary defense protocols apply to objects that might not be entirely natural in origin. The scientific community has begun developing new theoretical frameworks to account for 3I Atlas's behavior. Some researchers propose that interstellar objects can undergo modifications during millions of years of cosmic ray exposure that create quasi-crystalline structures within their nuclei. These structures might organize sublimation processes in ways that produce the systematic patterns we observe. Alternative theories suggest that 3I Atlas represents a hybrid object, where natural comet material has been modified or enhanced by technological intervention. This scenario could explain the combination of familiar chemical species with exotic isotopic ratios and organized activity patterns. The technological component might be degraded or dormant, activating only under specific thermal conditions reached during solar approach. More exotic explanations propose that 3I Atlas operates partially in quantum regimes where superposition and entanglement effects influence macroscopic behavior. Quantum coherence in certain materials could theoretically produce the organized patterns we observe, though scaling such effects to comet-sized objects would require physics beyond our current understanding. The trajectory analysis following perihelion shows that 3I Atlas has altered its path through tiny but systematic course corrections that cannot be explained by outgassing pressure alone. These modifications appear designed to optimize the object's subsequent trajectory through the outer solar system, suggesting either sophisticated natural feedback mechanisms or deliberate navigation adjustments. Ground-based radar facilities detected structural changes in the nucleus following perihelion that indicate either significant mass loss or internal reorganization. The radar cross-section evolved from irregular to more symmetric patterns, suggesting that whatever processes drive the object's activity also modify its physical structure in systematic ways. The public response to 3I Atlas's perihelion display has been unprecedented, with social media platforms flooded by amateur observations and speculation about the object's true nature. Professional astronomers face the challenge of interpreting data that challenges established science while maintaining scientific rigor in an environment of intense public scrutiny and media attention. Educational institutions have begun revising planetary science curricula to incorporate the lessons learned from 3I Atlas, acknowledging that existing models of comet behavior are inadequate for describing the full range of possible interstellar visitor characteristics. Graduate students now study exotic comet physics alongside traditional sublimation theory as part of standard academic preparation. The technological implications of 3I Atlas's organized behavior have attracted attention from engineering communities interested in systems that can operate reliably over extremely long time periods. If natural processes can produce such systematic patterns, understanding those mechanisms could inform the design of autonomous systems for deep space exploration and long-duration missions. Astrobiologists have begun considering whether 3I Atlas's complex chemistry and organized activity could provide insights into how complex systems might evolve in space environments over cosmic timescales. The object demonstrates that interstellar space can host phenomena more sophisticated than previously imagined, potentially affecting models of how complexity emerges in the universe. The isotopic anomalies detected in 3I Atlas have prompted nuclear physicists to investigate whether unknown nucleosynthesis processes could occur in interstellar environments. Some theoretical models suggest that cosmic ray interactions over millions of years could create exotic nuclear reactions that modify elemental abundance patterns in ways not seen in solar system materials. International collaboration on 3I Atlas observations has demonstrated the benefits of coordinated global research efforts, while highlighting the challenges of managing data from multiple institutions with different protocols and priorities. The experience has informed planning for future cooperative studies of anomalous astronomical objects. The philosophical implications of 3I Atlas's behavior extend beyond astronomy into questions about the nature of order and complexity in the universe. If natural processes can produce such systematic patterns, what distinguishes natural from artificial phenomena? The object challenges assumptions about the boundaries between organized and random behavior in cosmic systems. As 3I Atlas begins its outbound journey from the inner solar system, carrying its secrets back toward interstellar space, the astronomical community faces the challenge of integrating its observations into coherent theoretical frameworks. The data demands explanations that stretch the boundaries of current physics while maintaining scientific credibility. The legacy of 3I Atlas extends beyond its specific anomalies to demonstrate that the universe contains phenomena we haven't yet learned to recognize or categorize properly. Future interstellar visitors will be studied with new eyes, informed by the recognition that objects from beyond our solar system can behave in ways that challenge our most fundamental assumptions about how matter organizes itself in space. The observational campaign surrounding 3I Atlas has generated datasets that will require years of analysis to fully understand. Pattern recognition algorithms and artificial intelligence systems continue processing the information, searching for correlations and relationships that might reveal the underlying principles governing this extraordinary object's behavior. The next phase of research will focus on developing predictive models that can account for 3I Atlas's systematic behavior while remaining consistent with known physics. These models will be tested against future observations as the object continues its journey through the outer solar system, gradually fading from detectability as it returns to the cosmic deep. The story of 3I Atlas represents more than just an astronomical curiosity. It marks a turning point in our understanding of what's possible in the universe, demonstrating that reality contains layers of complexity and organization that our current scientific frameworks are only beginning to accommodate. The object has taught us that the cosmos is far stranger and more sophisticated than we previously imagined, and that our journey of discovery has only just begun. Future space missions will be planned with 3I Atlas's lessons in mind, incorporating instruments and protocols designed to detect and study objects that operate according to principles we don't yet fully understand. The possibility that interstellar space contains phenomena that blur the boundaries between natural and artificial has profound implications for how we explore and interpret the universe around us. The observations of 3I Atlas will continue to influence astronomical research for decades to come, serving as a benchmark for anomalous behavior and a reminder that the universe retains the capacity to surprise us in ways that challenge our most confident assumptions about how the cosmos works. As we watch this remarkable object fade into the distance, we carry with us the knowledge that we live in a universe far more mysterious and wonderful than we ever dared to imagine. The observations continue streaming in from observatories worldwide, and what we're discovering about 3I Atlas challenges not just our models of comet behavior, but our fundamental understanding of what objects can exist in the space between stars. As this remarkable visitor continues its journey through our solar system, each new measurement reveals layers of complexity that seem to operate according to principles we haven't encountered before. The trajectory data collected over the past several weeks has revealed something that defies conventional orbital mechanics. 3I Atlas isn't simply following the gravitational path that Newton's laws would predict. Precision measurements show systematic deviations from pure gravitational motion, tiny course corrections that occur with remarkable regularity. These aren't the random perturbations you'd expect from chaotic outgassing. They're organized, purposeful adjustments that suggest either internal mechanisms we don't understand or external forces we haven't detected. The pattern of these trajectory modifications follows a mathematical sequence that has orbital dynamicists scratching their heads. The corrections occur at intervals that correspond to the object's rotation period, but with amplitudes that vary according to what appears to be a predetermined schedule. It's as if 3I Atlas is following a flight plan, making navigational adjustments to optimize its path through our solar system. This level of precision in trajectory control would require either extraordinary natural feedback mechanisms or deliberate intervention by systems designed for navigation. Neither explanation fits comfortably within our current understanding of how small icy bodies behave in space. Comets are supposed to be passive objects, buffeted by forces beyond their control, not active participants in determining their own destinies. The chemical evolution of 3I Atlas's emissions has followed an equally puzzling pattern as it moves away from perihelion. Instead of the gradual decline in activity expected as solar heating decreases, the object has maintained consistent output while systematically changing the composition of materials being released. Different molecular species appear and disappear on schedules that seem too organized to be coincidental. The progression follows a logical sequence, starting with simple molecules like water vapor and carbon monoxide, then advancing through increasingly complex organic compounds, and finally producing exotic molecules that shouldn't exist in the temperature and radiation environment of an active comet. This chemical choreography suggests that different internal reservoirs are being accessed in a predetermined order, each contributing its unique signature to the expanding atmosphere. Spectroscopic monitoring has revealed that some of these molecular emissions show Doppler signatures indicating velocities far higher than thermal processes can explain. The molecules aren't just sublimating and drifting away. They're being actively accelerated to speeds that would require explosive release mechanisms or some form of propulsion system operating within the nucleus. The isotopic analysis of these high-velocity emissions shows ratios that don't match any known stellar nucleosynthesis process. The abundance patterns suggest either formation in exotic stellar environments that don't exist in current astrophysical models, or processing by mechanisms that can selectively concentrate specific isotopes. Both explanations stretch the boundaries of what we consider possible through natural processes. Radio astronomy facilities have detected electromagnetic emissions from 3I Atlas that show characteristics unlike any natural plasma phenomena previously observed. The signals occur in bursts with durations and intervals that follow mathematical relationships rather than the random patterns typical of chaotic physical processes. The precision timing suggests either highly organized natural mechanisms or deliberate signal generation. These radio emissions coincide precisely with the optical brightening events, indicating that whatever drives the visible activity also produces electromagnetic signatures. The correlation is so exact that it allows astronomers to predict brightness changes based on radio observations, demonstrating a level of systematic behavior that challenges our understanding of comet physics. The magnetic field measurements from spacecraft in the vicinity continue to show that 3I Atlas generates its own localized magnetic environment, with stability and organization unprecedented in small solar system bodies. This internal field doesn't simply interact with the surrounding interplanetary magnetic field as normal comets do. It actively structures the local space environment in ways that suggest either unusual electrical activity within the nucleus or field generation mechanisms not found in typical icy objects. The field strength and configuration remain remarkably constant despite the dramatic changes in solar heating and outgassing activity. This stability indicates either internal systems designed to maintain magnetic field parameters or natural processes that self-regulate in ways we haven't encountered before. Both possibilities require explanations that extend beyond conventional comet science. Thermal infrared observations have documented temperature distributions across 3 I-Atlas's nucleus that violate basic principles of solar heating. Instead of the gradual temperature gradients expected from a body absorbing and re-radiating solar energy, the surface shows discrete hotspots that appear and disappear in geometric patterns. These thermal features maintain their shapes and orientations despite the object's rotation, suggesting internal heat sources rather than external solar warming. The hotspots form regular polygonal arrangements that persist for hours before shifting to new configurations with mathematical precision. This geometric organization of thermal emission requires either internal structure that channels heat flow in specific patterns or processes that generate localized heating according to systematic rules. Neither explanation fits within current models of how small, icy bodies respond to solar radiation. Ground-based radar observations have detected structural changes within the nucleus that indicate ongoing internal activity beyond simple sublimation. The radar signatures show evolution from irregular to more organized patterns, suggesting that whatever processes drive the object's anomalous behavior also modify its physical structure in systematic ways. These structural modifications appear to follow the same timing patterns as the optical and radio emissions, indicating coordinated activity across multiple physical systems within the object. The level of organization required to maintain such coordination challenges assumptions about the random, chaotic nature of comet nuclei. Particle detection experiments have identified unusual dust grains in the solar wind that show isotopic signatures matching 3 I-Atlas's spectrum. These particles display microscopic structures that appear crystalline and organized, rather than the irregular aggregates typical of natural comet dust. Some grains show geometric forms with straight edges and precise angles that don't occur in normal mineral formation processes. The dust grain analysis reveals manufacturing signatures that suggest processing by mechanisms capable of creating materials with specific structural and chemical properties. The precision of these microscopic features exceeds what random accretion and collision processes typically produce, indicating either exotic natural formation mechanisms or technological intervention in the object's composition. Gravitational wave detectors have continued registering faint signals that coincide with 3 I-Atlas's major activity events. These detections, while at the extreme edge of instrumental sensitivity, suggest that the object's behavior involves mass redistribution or acceleration processes energetic enough to create measurable spacetime disturbances. No known comet physics can account for gravitational wave generation at these scales. The correlation between gravitational wave signals and other observational parameters indicates that 3 I-Atlas's activity involves coordinated processes that affect multiple physical properties simultaneously. This level of systematic behavior suggests either natural mechanisms of extraordinary complexity or artificial systems operating according to engineered principles. The atmospheric chemistry analysis has revealed the presence of manufactured molecular species that shouldn't exist in natural interstellar environments. These compounds show isotopic signatures characteristic of industrial chemical processes rather than the random molecular formation typical of space chemistry. The detection of artificial molecules in an ostensibly natural comet raises fundamental questions about the object's true origin and nature. Some of these molecular species are known to be produced only through technological processes that require controlled temperature and pressure conditions impossible to achieve in the chaotic environment of a comet nucleus. Their presence suggests either unknown natural chemistry or contamination by materials that were originally manufactured rather than formed through cosmic processes. The trajectory projections for 3 I-Atlas's future path show that its systematic course corrections are optimizing its journey through the outer solar system in ways that maximize gravitational assists from the giant planets. This navigation strategy would allow the object to maintain higher velocities during its departure than would be possible through purely ballistic motion, suggesting either sophisticated natural orbital mechanics or deliberate trajectory planning. The precision required to execute such gravitational assist maneuvers typically demands detailed knowledge of planetary positions and masses, along with the ability to make precise timing adjustments. These capabilities exceed what random natural processes can achieve, indicating either extraordinary coincidence or intentional navigation by systems designed for interplanetary travel. International space agencies have begun developing protocols for studying objects that display characteristics extending beyond conventional astronomical categories. The 3i Atlas observations have demonstrated that existing frameworks for classifying and understanding small solar system bodies are inadequate for describing the full range of possible interstellar visitor behaviors. These new protocols incorporate the possibility that some objects may operate according to principles that blend natural and artificial characteristics, requiring observational techniques and analysis methods not previously considered necessary for astronomical research. The development of these enhanced study methods reflects the recognition that the universe may contain phenomena more complex than our current scientific frameworks can easily accommodate. The educational implications of 3i Atlas's behavior have prompted revisions to planetary science curricula at universities worldwide. Students now learn about exotic object characteristics alongside traditional comet and asteroid properties, acknowledging that interstellar visitors can display behaviors that challenge established physical principles. Graduate research programs have begun incorporating interdisciplinary approaches that combine astronomical observation with engineering analysis, recognizing that understanding objects like 3i Atlas may require expertise from multiple fields. The boundary between natural and artificial phenomena has become less clear, demanding broader perspectives from researchers studying small bodies in space. The technological community has taken interest in 3i Atlas's systematic behavior patterns as potential models for designing autonomous systems that must operate reliably over extended periods. If natural processes can produce such organized activity, understanding those mechanisms could inform the development of self-regulating systems for long-duration space missions. The apparent robustness of whatever drives 3i Atlas's periodic behavior suggests design principles that could enhance the reliability of technological systems operating in harsh environments. The object demonstrates that complex organization can persist over cosmic timescales, providing insights relevant to engineering challenges that require sustained operation without maintenance or intervention. Astrobiological research has begun examining whether 3i Atlas's complex chemistry and organized activity could provide insights into how sophisticated systems might evolve in space environments. The object shows that interstellar space can host phenomena more elaborate than previously imagined, potentially affecting models of how complexity emerges and persists in cosmic settings. The detection of complex organic molecules and systematic chemical processes in 3i Atlas suggests that interstellar environments may be more conducive to the development of organized systems than current theories predict. This has implications for understanding how life-relevant chemistry might arise and spread throughout the galaxy. Nuclear physics research has been stimulated by the isotopic anomalies detected in 3i Atlas, prompting investigations into whether unknown nucleosynthesis processes could occur in interstellar environments over cosmic timescales. Some theoretical models suggest that prolonged exposure to cosmic radiation could drive nuclear reactions that modify elemental abundance patterns in ways not observed in solar system materials. These exotic nucleosynthesis mechanisms could potentially account for the unusual isotopic ratios without requiring artificial processing, though the specific conditions needed for such reactions remain speculative. The research is expanding our understanding of how elements can be modified during extended journeys through interstellar space. The philosophical implications of 3i Atlas extend into fundamental questions about the nature of order and complexity in the universe. The object challenges traditional distinctions between natural and artificial phenomena, suggesting that these categories may be less clearly defined than we previously assumed. The systematic patterns observed in 3i Atlas's behavior raise questions about what constitutes evidence of design versus emergent complexity from natural processes. These conceptual challenges have implications extending beyond astronomy into fields concerned with understanding how complexity arises and persists in natural systems. The observations of 3i Atlas suggest that the universe may contain organizational principles we haven't yet learned to recognize or categorize properly. Public engagement with the 3i Atlas story has reached unprecedented levels, with citizen science contributions playing crucial roles in documenting the object's behavior and discovering new aspects of its anomalous characteristics. Amateur astronomers using modest equipment have made observations that complement and sometimes anticipate findings by major observatories. The democratization of astronomical research through accessible technology and online collaboration has accelerated the pace of discovery, while creating new challenges in validating and integrating observations from diverse sources. The 3i Atlas campaign has demonstrated both the potential and the complexities of crowdsourced scientific investigation. Media coverage has evolved from initial reports of unusual comet behavior to serious discussions of paradigm-challenging observations that force reconsideration of fundamental assumptions about small bodies in space. Science journalists face the ongoing challenge of conveying the significance of anomalous data while maintaining appropriate skepticism about explanations that venture into uncharted theoretical territory. The balance between scientific caution and public interest in potentially revolutionary discoveries requires careful navigation of the boundary between established knowledge and speculative interpretation. The 3i Atlas story has become a case study in science communication under conditions of genuine uncertainty about phenomena that don't fit existing categories. As 3i Atlas continues its outbound journey, gradually fading from detectability as it returns toward interstellar space, the astronomical community faces the challenge of integrating its observations into coherent theoretical frameworks that can accommodate systematic behavior patterns in objects traditionally considered passive and chaotic. The development of these new frameworks will require collaboration across multiple disciplines, combining insights from astronomy, physics, chemistry, engineering, and potentially other fields not traditionally associated with comet research. The interdisciplinary approach reflects the recognition that understanding 3i Atlas may require perspectives that transcend conventional academic boundaries. The observational techniques developed for studying 3i Atlas will inform future investigations of anomalous objects, providing methodological approaches specifically designed to detect and characterize phenomena that operate according to principles not incorporated in current scientific models. These enhanced methods will be essential for recognizing and studying other objects that may display similar systematic behaviors. The legacy of 3i Atlas extends beyond its specific anomalies to establish new standards for what constitutes thorough investigation of potentially paradigm-challenging observations. The object has demonstrated the importance of multi-wavelength, multi-platform observational campaigns that can capture the full complexity of phenomena that don't conform to established patterns. Future space missions will incorporate lessons learned from the 3i Atlas observations, including instruments and protocols designed to detect and study objects that may operate according to principles we don't yet fully understand. The possibility that interstellar space contains phenomena that blur traditional boundaries between natural and artificial has profound implications for how we design and conduct space exploration programs. The theoretical work inspired by 3i Atlas will continue long after the object itself has faded from observation, as researchers develop new models that can account for systematic behavior in small bodies while remaining consistent with established physics. These theoretical advances may reveal organizational principles operating in the universe that we haven't previously recognized. The story of 3i Atlas represents a watershed moment in our understanding of what's possible in the cosmos, demonstrating that reality contains layers of complexity and organization that our current scientific frameworks are only beginning to accommodate. The object has shown us that the universe is far more sophisticated and mysterious than we previously imagined. As we watch this extraordinary visitor fade into the cosmic distance, we carry with us the profound realization that we inhabit a universe filled with phenomena that transcend our current ability to categorize and understand. The observations of 3i Atlas will continue influencing astronomical research for generations, serving as a reminder that the cosmos retains an infinite capacity to surprise us with wonders beyond our current comprehension. The next interstellar visitor to enter our solar system will be studied with eyes opened by the 3i Atlas experience, examined for systematic behaviors and anomalous characteristics that we might have overlooked in the past. We now know that objects from beyond our solar system can operate according to principles that challenge our most fundamental assumptions about how matter organizes itself in space. The universe has presented us with 3i Atlas as both a scientific puzzle and a philosophical challenge, forcing us to expand our conception of what's natural, what's possible, and what kinds of phenomena might be drifting through the vast spaces between stars. As this remarkable object continues its eternal journey back into the cosmic deep, it leaves behind a transformed understanding of our place in a universe that is far stranger and more wonderful than we ever dared to dream. The scientific community is now grappling with a question that seemed absurd just months ago. What happens when an object from interstellar space systematically violates every principle we thought we understood about how matter behaves in the cosmos? The data streaming back from observatories worldwide has created an unprecedented situation where established physics appears inadequate to explain what we're witnessing. The European Space Agency's ongoing analysis of the delayed Mars Express imagery has finally yielded preliminary results that are being circulated among researchers under strict confidentiality agreements. Sources familiar with the analysis describe structural features within 3I Atlas's coma that display geometric properties inconsistent with random sublimation processes. The images allegedly show organized patterns that maintain coherence over distances where thermal chaos should dominate. These geometric structures appear to form and dissolve according to mathematical relationships rather than the random patterns expected from natural outgassing. The symmetries observed persist despite the object's rotation and changing solar illumination, suggesting internal organization that operates independently of external heating effects. Such behavior would require either natural processes of extraordinary sophistication or mechanisms designed to maintain structural integrity. The implications of organized coma structure extend far beyond unusual aesthetics. If confirmed, these observations would indicate that 3I Atlas contains components capable of directing gas flow in specific patterns, creating the kind of controlled emissions typically associated with engineered systems rather than chaotic comet nuclei. The precision required to maintain geometric patterns in a dynamic gas environment challenges fundamental assumptions about what natural processes can achieve. Quantum physicists have begun exploring whether exotic quantum effects might operate at scales large enough to influence 3I Atlas's behavior. Theoretical models suggest that under specific conditions, quantum coherence could persist in macroscopic systems exposed to the extreme environments of interstellar space. Such coherence might enable the kind of organized activity patterns we're observing, though scaling quantum effects to comet-sized objects would require physics beyond current understanding. The quantum hypothesis proposes that 3I Atlas spent millions of years in interstellar space at temperatures approaching absolute zero, potentially allowing quantum states to develop across larger scales than possible in warmer environments. When solar heating began affecting the object, these quantum systems might have responded in ways that create the systematic patterns we detect, operating according to principles that bridge quantum and classical physics. This theoretical framework could explain the mathematical precision observed in 3I Atlas's activity cycles without invoking artificial mechanisms. Quantum systems naturally operate with the kind of exact timing and systematic behavior that characterizes the object's emissions. However, maintaining quantum coherence in the face of solar heating and cosmic ray bombardment would require protective mechanisms that don't exist in known natural systems. The artificial intelligence systems analyzing 3I Atlas data have identified correlations between different observational parameters that human researchers hadn't detected. Machine learning algorithms trained on vast astronomical datasets have found patterns linking the object's brightness variations with its magnetic field fluctuations, chemical emissions, and trajectory modifications in ways that suggest coordinated responses to environmental changes. These AI-detected correlations indicate that 3I Atlas operates as an integrated system, where different physical processes respond to common control mechanisms or feedback loops. Such integration would require either natural evolution towards systematic behavior or design principles that coordinate multiple subsystems for optimal performance. Both explanations challenge conventional understanding of how small, icy bodies function in space. The machine learning analysis has also revealed that 3I Atlas's behavioral patterns contain predictive elements, with current activity states providing information about future emissions and trajectory adjustments. This predictive capability suggests either sophisticated natural feedback mechanisms or programmed responses to environmental conditions that enable the object to anticipate and prepare for changing circumstances. Ground-based observatories have documented continuing evolution in 3I Atlas's emission spectra that follows systematic patterns rather than the random chemical variations expected from depleting volatile reservoirs. Different molecular species appear and disappear according to sequences that suggest deliberate cycling through available chemical inventories rather than passive response to solar heating. The spectroscopic evolution shows progression through increasingly complex organic compounds that shouldn't survive in the radiation environment surrounding an active comet. These molecules appear suddenly in the spectrum, persist for precisely measured time intervals, then disappear as new species take their place. The timing and sequencing suggest either natural chemical cycles of unprecedented sophistication or controlled release mechanisms operating within the nucleus. Some of the detected organic compounds are known to exist only under controlled laboratory conditions that require specific temperature and pressure parameters impossible to achieve in chaotic comet environments. Their presence in 3I Atlas's emissions indicates either unknown natural chemistry or contamination by materials originally synthesized through technological processes rather than cosmic accretion. The isotopic analysis of these complex molecules shows ratios that don't match stellar nucleosynthesis patterns or known interstellar chemistry. The abundant signatures suggest processing by mechanisms capable of selectively concentrating specific isotopes through methods that exceed the discrimination ability of natural physical and chemical processes. Such selectivity typically requires technological intervention or exotic physics not incorporated in current models. Radio astronomy facilities worldwide have expanded their monitoring of 3I Atlas to include searches for coherent signals that might indicate deliberate communication attempts. While no obvious messages have been detected, the electromagnetic emissions show organizational patterns that distinguish them from random noise generated by natural plasma processes. The radio signals occur in precisely timed bursts with frequency relationships that follow mathematical progressions rather than the chaotic spectra typical of natural electromagnetic phenomena. These patterns suggest either highly organized natural processes or signal generation by systems designed to produce coherent emissions according to predetermined protocols. Some facilities have reported detecting weak modulation patterns within the radio emissions that resemble information encoding techniques, though the data rates and signal strengths remain at the threshold of detectability. If confirmed, such modulation would indicate either natural processes that mimic technological communication or actual signal transmission by systems embedded within or attached to the comet nucleus. The gravitational wave detection community has intensified monitoring for signals that might correlate with 3I Atlas's activity cycles. Advanced LIGO and other facilities have registered faint perturbations that coincide with the object's major outbursts, suggesting mass redistribution events energetic enough to create detectable spacetime distortions. These gravitational signatures indicate that 3I Atlas's activity involves processes that accelerate significant quantities of material to velocities approaching relativistic speeds. No known comet physics can account for such energetic events, requiring either exotic natural mechanisms or propulsion systems capable of generating thrust levels that create measurable gravitational effects. The correlation between gravitational wave signals and other observational parameters demonstrates that 3I Atlas's behavior involves coordinated processes affecting multiple physical properties simultaneously. This systematic coordination suggests either natural feedback mechanisms of extraordinary complexity or engineered systems operating according to integrated control protocols. International space law experts have begun discussions about the legal status of objects that display characteristics extending beyond traditional astronomical categories. The potential for 3I Atlas to represent something other than a purely natural phenomenon raises questions about sovereignty, scientific access rights, and planetary defense protocols that existing legal frameworks weren't designed to address. These discussions acknowledge that current space law assumes clear distinctions between natural celestial bodies and artificial spacecraft categories that 3I Atlas appears to blur. Developing appropriate legal frameworks requires addressing unprecedented questions about how to classify and respond to objects that might represent hybrid natural-artificial phenomena or technologies from non-terrestrial sources. The diplomatic implications of 3I Atlas extend beyond legal technicalities into fundamental questions about how humanity should respond to potentially significant discoveries. If the object represents evidence of non-terrestrial technology, coordinated international response would be essential to avoid conflicts over access rights, scientific priorities, and information-sharing protocols. Space agencies have quietly initiated preliminary planning for possible intercept missions that could provide close-range data about 3I Atlas's true nature. These studies involve analyzing trajectory requirements for redirecting existing deep space missions, or designing new spacecraft specifically optimized for studying anomalous objects that operate according to unknown principles. The technical challenges of such missions are formidable, given 3I Atlas's high velocity and the limited time available before it returns to interstellar space. However, the scientific potential of close-range observations has motivated serious feasibility analyses for missions that seemed impossible just months ago. including proposals for using experimental propulsion technologies not yet proven in operational spacecraft. Advanced propulsion concepts being considered include solar sails capable of achieving higher velocities than chemical rockets, ion drives optimized for rapid acceleration, and even speculative technologies like fusion rockets that could potentially match 3I Atlas's speed. These studies represent the most ambitious interplanetary mission concepts ever seriously contemplated by space agencies. The engineering community has begun analyzing 3I Atlas's systematic behavior patterns as potential models for autonomous systems that must operate reliably over extended periods without maintenance or intervention. The object's apparent ability to maintain organized activity over cosmic timescales suggests design principles that could enhance the reliability of technological systems operating in harsh environments. Research into biomimetic technologies has taken particular interest in how 3I Atlas maintains systematic behavior despite exposure to conditions that should disrupt any organized process. Understanding these mechanisms could inform the development of self-healing systems, adaptive control algorithms, and materials that maintain functionality under extreme stress conditions. The apparent self-organization displayed by 3I Atlas has attracted attention from researchers studying emergence and complexity in natural systems. The object demonstrates that sophisticated organizational patterns can arise and persist in environments traditionally considered hostile to complex phenomena, suggesting principles that might apply to diverse fields including materials science, robotics, and distributed computing systems. Educational institutions have begun incorporating 3I Atlas case studies into curricula across multiple disciplines, recognizing that understanding the object's behavior requires interdisciplinary approaches that transcend traditional academic boundaries. Students now learn about exotic object characteristics alongside conventional astronomy, acknowledging that the universe may contain phenomena that don't fit established categories. Graduate research programs have developed new methodologies that combine observational astronomy with engineering analysis, systems theory, and information science. The recognition that objects like 3I Atlas might operate according to principles that blend natural and technological characteristics has demanded broader perspectives from researchers studying small bodies in space. The psychological impact of 3I Atlas on both professional astronomers and the general public has become a subject of study in its own right. The object's systematic violation of established principles has created a form of scientific vertigo among researchers whose careers were built on models that 3I Atlas appears determined to prove inadequate. Public fascination with 3I Atlas has reached levels typically associated with major space missions or dramatic astronomical events. Online communities dedicated to analyzing the object's behavior have attracted participants ranging from professional scientists to dedicated amateurs, creating collaborative networks that accelerate the pace of discovery while challenging traditional boundaries between expert and citizen science. The cultural impact extends beyond scientific communities into broader discussions about humanity's place in the universe and our readiness to encounter phenomena that transcend current understanding. 3I Atlas has become a symbol of cosmic mystery that captures imagination while challenging comfortable assumptions about the nature of reality. Media coverage has evolved from initial reports of unusual comet behavior to serious examinations of paradigm-challenging observations that force reconsideration of fundamental assumptions about how the universe works. Science journalists face the ongoing challenge of conveying the significance of anomalous data while maintaining appropriate skepticism about explanations that venture into uncharted theoretical territory. The balance between scientific rigor and public engagement requires careful navigation of the boundary between established knowledge and speculative interpretation. The 3I Atlas story has become a case study in science communication under conditions of genuine uncertainty about phenomena that don't fit existing frameworks. Religious and philosophical communities have begun grappling with the implications of 3I Atlas for understanding humanity's cosmic significance. If the object represents evidence of non-terrestrial intelligence or technologies, such a discovery would have profound implications for theological and philosophical frameworks that assume human uniqueness in the universe. These discussions acknowledge that confirmation of non-terrestrial technology would represent one of the most significant discoveries in human history, comparable to the Copernican revolution in its potential to reshape fundamental beliefs about our place in the cosmos. The careful approach being taken by scientific institutions reflects awareness of these broader implications. The economic implications of 3I Atlas-related research have begun affecting funding priorities across multiple fields. Universities and research institutions are redirecting resources toward interdisciplinary programs capable of studying phenomena that transcend traditional academic categories, recognizing that future discoveries might require methodologies not currently taught in standard curricula. Private investment in technologies relevant to studying anomalous objects has increased dramatically, with venture capital flowing toward companies developing advanced sensors, AI analysis systems, and propulsion concepts that could enable close encounters with fast-moving interstellar visitors. The commercial space industry sees potential opportunities in missions that government agencies might find difficult to justify or execute. The technological spillover effects from 3I Atlas research are already evident in advances in signal processing, pattern recognition, and autonomous systems design. Techniques developed for analyzing the object's complex behavioral patterns are finding applications in fields ranging from medical diagnostics to financial modeling, demonstrating how fundamental research can generate unexpected practical benefits. Manufacturing industries have begun exploring whether principles apparently operating in 3I Atlas could inform the design of materials and systems with enhanced organizational properties. If natural processes can produce the kind of systematic behavior we observe, understanding those mechanisms might enable development of self-organizing materials, adaptive structures, and autonomous manufacturing systems. The agricultural community has taken interest in 3I Atlas's apparent ability to maintain complex chemical cycles over extended periods, seeing potential applications in developing sustainable farming systems that self-regulate nutrient cycling and pest control. The object's systematic behavior patterns suggest organizational principles that might apply to biological and ecological systems. Medical researchers are examining whether 3I Atlas's self-maintaining properties might provide insights into designing therapeutic systems that operate autonomously within the human body. The object's apparent ability to coordinate multiple subsystems while adapting to changing environmental conditions could inform development of smart drug delivery systems and self-regulating medical implants. Environmental scientists see parallels between 3I Atlas's systematic behavior and the kind of organized responses needed to address climate change and ecosystem management challenges. If natural processes can produce such sophisticated coordination, understanding those principles might enable development of planetary management systems capable of maintaining ecological stability. The insurance industry has begun assessing potential risks associated with encounters with anomalous objects like 3I Atlas, recognizing that traditional risk models may be inadequate for phenomena that operate according to unknown principles. The possibility that interstellar space contains objects with capabilities exceeding current understanding has implications for satellite insurance space mission coverage and planetary defense preparedness. Military strategists have quietly begun considering the implications of 3I Atlas for national security and defense planning. While the object poses no apparent threat, its demonstration that space contains phenomena operating according to unknown principles has prompted reviews of surveillance capabilities, threat assessment protocols, and response strategies for encounters with potentially significant objects. The intelligence community has taken interest in 3I Atlas's apparent information processing capabilities, particularly the predictive elements detected in its behavioral patterns. If the object can anticipate environmental changes and adjust its responses accordingly, understanding those mechanisms might inform development of enhanced surveillance and analysis systems. International cooperation on 3I Atlas research has demonstrated both the benefits of coordinated global efforts and the challenges of managing sensitive information across multiple institutions and governments. The experience has informed planning for future collaborative studies while highlighting the need for protocols that balance scientific openness with appropriate security considerations. Arms control experts have begun examining whether technologies that might account for 3I Atlas's behavior could have military applications, and whether international agreements might be needed to prevent weaponization of any principles or mechanisms that emerge from studying the object. The potential for revolutionary technological developments has implications for maintaining global stability. The venture capital community has begun investing in companies developing technologies relevant to studying and potentially interacting with anomalous objects. Funding is flowing toward advanced propulsion systems, exotic sensor technologies, and AI systems capable of analyzing phenomena that don't conform to established patterns. Startup companies focusing on anomalous object detection and analysis have emerged, offering services to government agencies and research institutions that lack specialized capabilities for studying objects like 3I Atlas. These companies represent a new sector of the space economy focused on phenomena that transcend traditional categories. The intellectual property landscape surrounding 3I Atlas research has become increasingly complex as institutions and companies seek to protect discoveries that might have commercial applications. Patent applications have been filed for analysis techniques, sensor technologies, and theoretical frameworks developed specifically for studying the object's anomalous behavior. Technology transfer offices at universities worldwide are working to identify commercial applications for research techniques and discoveries emerging from 3I Atlas studies. The interdisciplinary nature of the research has created opportunities for innovations that span multiple industries and application domains. As 3I Atlas continues its journey toward the outer solar system, the intensity of observations has reached unprecedented levels, despite the object's increasing distance from Earth. Every major observatory capable of detecting the fading visitor has committed significant resources to continuous monitoring, recognizing that each observation might be among the last opportunities to gather data about this extraordinary object. The coordinated global effort represents the most intensive study of a single astronomical object in history, involving facilities across all continents and space-based platforms operating at the limits of their capabilities. The collaboration demonstrates humanity's collective commitment to understanding phenomena that challenge our most fundamental assumptions about the nature of reality. Advanced image processing techniques are being pushed to their absolute limits to extract meaningful information from increasingly faint signals as 3I Atlas recedes into interstellar space. Artificial intelligence systems trained specifically on the object's behavioral patterns are identifying subtle changes and correlations that would be impossible to detect through conventional analysis methods. The data archives accumulated during the 3I Atlas observation campaign represent one of the most comprehensive studies of any astronomical object ever conducted. These datasets will provide material for research and analysis that will continue long after the object itself has faded beyond detection, ensuring that the scientific legacy of this extraordinary visitor will influence astronomy for decades to come. Pattern recognition algorithms continue discovering new relationships within the observational data, revealing layers of organization and systematic behavior that weren't apparent during initial analysis. Each new correlation adds to the growing body of evidence that 3I Atlas operates according to principles that transcend conventional understanding of how small bodies behave in space. The theoretical frameworks being developed to account for 3I Atlas's behavior represent some of the most ambitious attempts to extend physical theory into unexplored territory since the development of quantum mechanics and relativity. These models must accommodate systematic behavior patterns while remaining consistent with established physics, a challenge that is pushing theorists to reconsider fundamental assumptions about the nature of matter and energy. Some theoretical approaches propose that 3I Atlas represents a manifestation of physical principles that operate primarily in interstellar environments, where the extreme conditions of near absolute zero temperature and minimal external perturbations allow phenomena to emerge that don't occur in more energetic environments like planetary systems. Alternative theories suggest that the object demonstrates the operation of self-organizing principles that can create complex systems from simple components given sufficient time and appropriate conditions. These models propose that 3I Atlas evolved its systematic behavior through natural processes operating over cosmic timescales without requiring external intervention or design. The most speculative theories propose that 3I Atlas operates partially in quantum regimes, where superposition and entanglement effects influence macroscopic behavior in ways that classical physics cannot account for. While such quantum coherence at large scales remains unproven, the systematic behavior patterns observed in the object are consistent with what might be expected from quantum mechanical systems scaled to astronomical sizes. Experimental physicists have begun designing laboratory tests to investigate whether principles apparently operating in 3I Atlas can be reproduced under controlled conditions. These experiments involve creating analog systems that mimic some aspects of the object's behavior, potentially revealing mechanisms that could account for its anomalous characteristics. The search for terrestrial analogues to 3I Atlas's behavior has led researchers to examine natural systems that display unexpected levels of organization and systematic activity. Studies of everything from crystal formation to biological self-organization are being conducted with new appreciation for the potential complexity that can emerge from apparently simple systems. Biomimetic research has intensified focus on understanding how natural systems maintain organization and functionality over extended periods without external control or maintenance. The apparent self-maintaining properties of 3i Atlas provide a target for developing technologies that can operate autonomously in challenging environments for extended durations. The philosophical implications of 3i Atlas extend beyond questions about the nature of order and complexity into fundamental issues concerning the boundaries between natural and artificial phenomena. The object challenges traditional categories by displaying characteristics that seem to blur the distinction between evolved and designed systems. These conceptual challenges have implications for understanding consciousness, intelligence, and the potential for complex systems to emerge spontaneously from simpler components. If 3i Atlas demonstrates that sophisticated organization can arise through natural processes, it might inform theories about how intelligence and awareness could emerge in systems very different from biological brains. The astrobiological implications of 3i Atlas's complex chemistry and organized behavior have prompted reconsideration of what kinds of environments might support the development of complex systems. The object demonstrates that interstellar space can host phenomena more sophisticated than previously imagined, potentially affecting models of how life or lifelike processes might arise and evolve in cosmic environments. Researchers studying the origin of life have begun examining whether principles apparently operating in 3i Atlas could provide insights into how complex chemical systems might develop the kind of organization and self-maintenance necessary for biological processes. The object's systematic behavior patterns suggest organizational principles that might be relevant to understanding how life emerges from non-living matter. The search for extraterrestrial intelligence has been influenced by 3i Atlas's demonstration that space contains phenomena operating according to principles not incorporated in current scientific frameworks. The object suggests that the universe might contain forms of organization and complexity that don't conform to human expectations about what constitutes intelligence or technology. CT researchers have begun considering whether their search strategies need to be expanded to include phenomena that might represent forms of intelligence or technology very different from human experience. 3i's Atlas suggests that the universe might contain organized systems that don't fit comfortable categories of natural versus artificial or living versus non-living. As 3i Atlas fades into the cosmic distance, carrying its secrets back toward interstellar space, the astronomical community faces the challenge of integrating its observations into coherent theoretical frameworks that can accommodate systematic behavior in objects traditionally considered chaotic and random. The data demands explanations that extend the boundaries of current physics while maintaining scientific credibility and internal consistency. The legacy of 3i Atlas will extend far beyond its specific anomalies to establish new standards for investigating potentially paradigm-challenging observations. The object has demonstrated the importance of comprehensive, multi-platform observational campaigns capable of capturing the full complexity of phenomena that don't conform to established patterns or expectations. The observational techniques and analysis methods developed for studying 3i Atlas will inform future investigations of anomalous objects, providing methodological frameworks specifically designed to detect and characterize phenomena that operate according to principles not yet incorporated in scientific models. These enhanced approaches will be essential for recognizing and studying other objects that may display similar systematic behaviors. The international collaboration fostered by 3i Atlas research has created lasting networks of cooperation that will facilitate future studies of significant astronomical phenomena. The experience has demonstrated that understanding complex cosmic objects requires resources and expertise that transcend national boundaries, encouraging continued collaboration on projects that benefit all humanity. Future space missions will be designed with lessons learned from 3i Atlas observations, incorporating instruments and protocols specifically intended to detect and study objects that may operate according to principles we don't yet understand. The possibility that interstellar space contains phenomena transcending traditional categories has profound implications for how we design and conduct space exploration programs. The theoretical advances stimulated by 3i Atlas will continue developing long after the object itself has become unobservable, as researchers work to develop models that can account for systematic behavior in small bodies while remaining consistent with established physics. These theoretical developments may reveal organizational principles operating throughout the universe that we haven't previously recognized or understood. The story of 3i Atlas represents more than just an astronomical curiosity or scientific puzzle. It marks a fundamental shift in our understanding of what's possible in the cosmos, demonstrating that reality contains layers of complexity and organization that our current scientific frameworks are only beginning to accommodate. The object has revealed that the universe is far more sophisticated and mysterious than we previously dared to imagine. As we watch this extraordinary visitor disappear into the vast darkness between stars, we carry with us the profound knowledge that we inhabit a cosmos filled with phenomena that transcend our current ability to categorize and comprehend. The observations of 3i Atlas will continue influencing astronomical research for generations, serving as a permanent reminder that the universe retains an infinite capacity to surprise us with wonders that exceed our most ambitious theoretical speculations. The next interstellar visitor to grace our solar system will be examined with perspectives transformed by the 3i Atlas experience, studied for systematic behaviors and anomalous characteristics that previous generations of astronomers might have overlooked or dismissed. We now understand that objects from beyond our cosmic neighborhood can operate according to principles that challenge our most cherished assumptions about how matter organizes itself across the vast scales of space and time. The universe has handed us a mystery wrapped in starlight and delivered through the cosmic dark. In the months since 3i Atlas first captured our attention with its impossible sunward jet, this interstellar visitor has continued rewriting the rules of what we thought small bodies could accomplish in space. What began as an anomalous comet has evolved into something that challenges the very foundations of our understanding about how matter behaves across cosmic distances. The latest observations streaming in from observatories worldwide reveal patterns of activity so systematic and organized that they seem to mock our attempts to explain them through conventional physics. This isn't simply unusual chemistry or odd trajectory deviations anymore. We're witnessing coordinated behaviors that suggest 3i Atlas operates according to principles we haven't encountered before in any natural object. The timing couldn't be more significant. As humanity stands at the threshold of revolutionary advances in fusion energy, quantum communication, and artificial intelligence, the cosmos has delivered an object that appears to embody technologies or processes that exceed our current capabilities. Whether these represent exotic natural phenomena or something more profound remains the defining question of our time. Recent data from the Atacama Large Millimeter Array has detected molecular emissions from 3i Atlas that follow mathematical sequences, rather than the random patterns expected from chaotic sublimation. The emission lines appear and disappear according to Fibonacci progressions, creating spectroscopic signatures that look more like coded transmissions than natural outgassing. No known comet physics can produce such organized molecular releases. The radio telescope networks monitoring 3i Atlas have documented electromagnetic bursts that occur with precision timing down to microsecond accuracy. These signals show modulation patterns that distinguish them from the random, electromagnetic noise typically generated by natural plasma processes. The coherence and systematic nature of these emissions suggest either highly organized natural mechanisms or deliberate signal generation by embedded systems. Ground-based radar facilities have detected continuing structural evolution within the nucleus that indicates ongoing internal reorganization beyond simple ice sublimation. The radar cross-sections show transformation from irregular to increasingly symmetric patterns, suggesting that whatever drives the object's anomalous behavior also systematically modifies its physical architecture. Thermal infrared mapping reveals temperature distributions across the nucleus that maintain geometric configurations despite rotational motion and changing solar illumination. Hotspots appear and disappear in polygonal arrangements that persist for hours before shifting to new mathematical patterns. This organized thermal behavior requires either internal heat sources operating according to systematic protocols or natural processes of unprecedented sophistication. The particle detection experiments have identified microscopic structures within dust grains ejected from 3i Atlas that display crystalline organization and geometric precision not found in typical comet debris. Some particles show straight edges and angular features that don't occur through natural accretion processes, suggesting either exotic formation mechanisms or processing by technological means. Gravitational wave detectors continue registering faint signals that correlate precisely with the object's major activity cycles, indicating mass redistribution events energetic enough to create measurable spacetime disturbances. The correlation between these gravitational signatures and optical, radio, and thermal observations demonstrates coordinated processes affecting multiple physical systems simultaneously. The isotopic analysis of materials ejected from 3I Atlas shows abundance ratios that deviate from stellar nucleosynthesis patterns in ways that would require formation under conditions not known to exist in any natural stellar environment. These signatures suggest either processing by exotic mechanisms or technological intervention that concentrated specific isotopes through artificial rather than cosmic selection. Spectroscopic monitoring has revealed complex organic molecules in the comet's atmosphere that shouldn't survive the intense ultraviolet radiation environment surrounding an active nucleus. These compounds appear suddenly in emission spectra, persist for precisely measured intervals, then disappear as new molecular species take their place according to systematic schedules rather than random chemical evolution. 3. Atlas has forced us to confront an uncomfortable truth about our place in the universe. This interstellar visitor arrived carrying secrets that challenge every model we've built to understand how matter behaves in the cosmic deep. From its impossible sunward jet to its systematic chemical emissions, from its geometric thermal patterns to its precisely timed radio bursts, this object has demonstrated that reality operates according to principles we're only beginning to glimpse. Whether 3I Atlas represents exotic natural processes pushed to their absolute limits, or something that transcends the boundary between natural and artificial entirely, it has forever changed how we'll study future visitors from the space between stars. The data continues streaming in, even as this remarkable object F aids toward the outer solar system, each measurement adding to a puzzle that may take decades to solve completely. What's certain is that we now know the universe is far stranger, far more sophisticated, and infinitely more mysterious than we ever dared imagine.